Alrighty, folks, so jumping into lesson 2, which is actually the last lesson for chapter 10, okay? We're going to be looking here, like I mentioned in the previous lesson. Again, in the last lesson, we talked about how opposites attract and like repel, right? Positive and positive will repel, positive and negative will attract, negative and negative will repel. And that idea of repelling and attracting, you know, as physics students, we're talking about forces there, right? That's a push or a pull. Repelling is pushing each other away. Attracting is pulling each other together. Those are forces. So the question naturally kind of came up in physics, is there a way to calculate how much force two charged objects will feel towards each other? Okay, and that is what we're going to start looking at in this lesson here, because it turns out there is. Okay, so again, we know that opposite charges attract and like charges repel, and that's a force. So can we quantify how much force, depending on how much charge we have and how far apart they are and things like that? And that's the exact question that a physicist by the name of Augustin de Coulomb, I'm butchering that, it's a very French name, okay? That's the question that they set out to answer with this experiment that we're going to start out with talking about today. So he determined the equation for the force between two charged objects, we should say there, two charged objects, using what's called a torsion balance, which you've actually seen a torsion balance before in Physics 20. It's pretty much the exact same experimental setup as the Cavendish experiment. Do you remember that one? That's the one that gave us the law of universal gravitation. That is this equation here. Fg, the force of gravity, is equal to the gravitational constant times the masses of the two objects that are exerting a force of gravity on each other divided by the distance between them squared. And so you might remember, right, in the Cavendish experiment, essentially what Cavendish did is took two heavy objects. Basically, you can think of them like bowling balls. I think they were actually made of iron, right? But heavy objects, and then put another heavy brick nearby, and he actually let the force of gravity between them kind of twist this arm. It's very low friction, very easy for it to twist, and then measured how much twisting force there was. And then, like any good experiment, he manipulated some variables to see how that amount of force depended. So the first thing he tested was if I use different masses, how is the force affected, right? If I make the mass 2 times larger, what happens to the force? If I make the mass half as large, what happens to the force? If I make the mass 4 times bigger, what happens to the force? Etc., etc., etc. Recorded all his data, looked at the relationships, probably made some graphs, and this is the relationship he worked out. He found that the force of gravity between two objects was equal to their masses multiplied together. And then he did another experiment where this time it was the same setup, but different manipulated variable. Then he varied the distance in between them. And he found that it was inversely proportional. The force of gravity acting between the two objects was inversely proportional to the distance between them squared. So moving them 2 times further apart actually made the force 4 times weaker, right? Inversely proportional to the distance squared. Moving them 3 times further would have made the force 9 times weaker because of that squared. Okay, so I'm still talking about Cavendish and gravity, but I wanted to remind you of that because now you'll be able to see, right, how similar Coulomb's experiment is to determine the relationship between the electric force and charge, right? So Cavendish was looking at the relationship between the gravitational force and mass and the distance between them. Coulomb's looking at the relationship between the electric force and charge, and also the distance between them. Now, I've put a link to a video in the description to this video if you're watching it on YouTube. If you are in the Google Classroom, just right-click it and open a new tab, and it should bring you to the YouTube one. I am going to go through and explain this in words, but the video might give you a nice visual to kind of see what's going on. It's a little bit of like a kind of a janky video, but it does do a good job of helping you visualize the Coulomb experiment. So I would recommend pausing this, watching that really quick, and then I'll come back and I'll break it down a little bit more. So here's the idea, okay? Essentially what he did is he got two things that he knew had the same charge type on them, right? So maybe they were both negative, both positive, whatever, but he knew they were the same. You know how we could have done this, right? He might have used conduction. In fact, he did use conduction. Remember from the previous lesson, when you touch two objects together, their charge kind of evens out and meets in the middle, and they end up with identical charges. So maybe he charged this thing and then touched it to that thing, right? So that he knew they had the same type of charge after doing that, okay? And then what he did, it's hooked up to like basically it twists on a spring here, and then this spring, the more it twists, the more tension you get. And then what you can do up here, there's a little knob on it basically, and you adjust the knob and it fights however hard this is pushing. And so you know that when you've returned it back to where it started, right, you are pushing on it just as hard as it is trying to push back. And therefore you've found the force it's pushing with, right? So since these have the same charge, what are they going to do? They're going to repel, right? So you can see that this would be, they're both negative in this example. So this would be like feeling a force like that, pushing it away from this negative object, right? And that pushing force there is going to cause this up here to want to twist, okay, with some force. Some force is causing it to twist. And then if you adjust it to push back on it until you've returned it back to where it started, you now know exactly how hard you're pushing on it to match the force it's pushing on you with, and there you go. What have you just figured out? You figured out how much force this is pushing this with. And that's what Coulomb wanted to work out. What's the relationship between the charges on these and the amount of force in newtons that they actually feel repelling each other because of that? Now, like any good experiment, right, you can't just do one trial and call it a day. He's trying to come up with the relationship overall between how when you change the charges, how does the resulting force change in response to that, right? So what he did was he manipulated the amount of charge on this sphere, or on this sphere. I'm not sure which one he actually manipulated, right? But the way he did that, incredibly simple. He actually just took it out and he touched it to a neutral object, right? And if you touch this to a neutral object, we know from the previous lesson that its charge will be cut in half, right? Remember, they're going to meet in the middle. So like whatever charge this had, if we just call it Q, it could be any number, we're going to touch it to another neutral object with a charge of 0, and then we'll divide by 2 because there's two objects. We're finding the midpoint of those two. So what do you get? You get half as much charge, right? So kind of a simple way to manipulate the charge. He took this out. This is all insulating, so he can touch this part without the charge just transferring into him, touches it to something neutral, and then puts it back in, and now he knows this has half the charge it had before. And then you repeat. You see, okay, so now how much do they repel? And he records how much the force is required up here, right? And there you go. You've now got the force when the charge was half as big as your first trial. Do it again. Take this out, touch it to another neutral object. It's now been cut in half another time, a quarter of what we started with, right? Do it all over again. Let them repel. See how much force you get. And you do that enough times, you know, you record all your data, you make a graph, and you can start to see the trend between the force between these two identically charged objects and the amount of charge that's on them, okay? And what he came up with was this. Now, this is not the equation. This is the relationship. So I'm not saying that the electric force equals this, but this is the proportionality. This is how it depends on the charges. So after doing this experiment, Coulomb came up with this. What this is saying is that the electric force is directly proportional to the product of the two charges. So charge 1 and charge 2 are exerting forces on each other, might be attractive, might be repulsive, okay? Multiply those charges together, and that is directly proportional to the force they feel. So this is just a piece of the relationship. It's not the entire equation. No one's saying that the force equals these, but they're part of the relationship, okay? And what this tells us is, all right, so like if we were to double the charges, right, we would double the force. If we were to cut the charges in half, we would cut the force in half. So we could say that the electric force is directly and linearly proportional to the product of the charges involved. All right. But Coulomb and physicists in general, of course, knew that there was more to it than just that, right? It was also going to depend on how close together they were, right? I mean, you can feel this like if you rub a balloon and you give it an electric charge. When it's close to your head, you can feel it pulling on you or sticking to you or making your hair stand up, right? But when it's far away, you can't really. So they knew there was something to do with the distance between them as well, which makes sense, right? I mean, that's kind of intuitive. The closer together, you would expect the force to be stronger, probably. So Coulomb did that next. He then manipulated the variable of how far apart are the two charges, right? And that one's even easier to manipulate. So now you would want to control this variable. You'd want to keep the same charges on them the whole time. And now you just do the same thing, but you move it further and further or closer and closer and do the same thing. Record how much force ends up being required, okay? And therefore how much force is between the two charged objects. And what Coulomb came up when he did that, again, this is not the equation, but it is the relationship between them. He found that the electric force was inversely proportional to the distance between them. That's the R. R is the distance between the charges. Okay. It was inversely proportional to the distance between them squared. Again, inversely proportional means when one gets larger, the other one gets smaller, right? And that's how we can represent that. Fe isn't proportional to r squared, it's proportional to 1 over r squared. So you can see from this, it suggests that as r gets bigger, the electric force gets smaller, right? We're dividing by a bigger number, we're going to get a smaller answer. And vice versa. If this gets smaller, the force gets bigger. Dividing by a smaller number gives us a bigger answer, okay? But not only does it depend on not only is it inversely proportional to r, it's inversely proportional to r squared, much like the gravitational law, Fg equals gmm over r squared, right? So what that means, again, remember, if we double r, we don't make Fe 2 times smaller. We make it 4 times smaller, right? Because r is getting squared. So, if r goes from 1 meter to 2 meters, we're now dividing by not 1 over 2, right? It's 1 over 2 squared, 1 over 4, right? 2 squared is 4. So it's an inverse square relationship. Now, if you put those two relationships together, that the electric force is directly proportional to the product of the two charges involved, and inversely proportional to the square of their separation distance, you can see this coming out, right? It depends on both of those things. So if we wanted to combine both of those into a single relationship, we could say this. It's proportional to the product of the charges, right? Making these larger will make the force larger. But it's also inversely proportional to the separation distance squared, right? Making the distance between them larger will make this smaller. And not only will it make it smaller, it'll make it smaller by a factor of however we change the distance squared, right? Tripling this will actually divide this by 9, okay? Now, this, once again, is not an equal sign, right? But this is actually the relationship. In terms of the variables we can actually change and the relationships that are going on and what the electric force actually depends on, this is the relationship. It depends on their charges and it depends on how far apart they are, okay? However, when Coulomb actually sat down and did this, and this is how we come up with these constants, when Coulomb sat down and did all the math, he said, okay, this is what it depends on. When we make the graph, it's clear. Doubling this doubles that. Doubling this cuts this in a quarter, right? And he did that over and over. But when you actually sit down and put in the numbers and calculate it out, you're always off, and you're always off by the same factor, okay? And that is just because of the fact that, keep in mind, all of these units that we use, like meters, right? There's nothing special about meters. That's a weird unit that humans came up with because it fit the world we were living in well, and we stuck with it, right? Coulombs, there's nothing special about coulombs for measuring charge. That's the unit we came up with. Newtons are in terms of kilograms, meters, and seconds. There's nothing special about kilograms, meters, or seconds, right? So there's no reason that this should give us the exact right answer, but it does give us the correct relationship. So we're always off by some number. If you multiply, if you put in the numbers, right, for the charge 1, charge 2, and divide by the distance between them squared, you're always off by the same factor. And that factor is this here. So this is just what we call a proportionality constant, okay? So all I'm saying here is that this is really the relationship. This is how we could change the electric force. We could do it by changing the charges or by changing the distance between them. It's just that putting in those numbers isn't going to give you the exact right answer. You need to then multiply them by what's called a proportionality constant. Now notice the key word there, constant. Sometimes students will say to me, I'm trying to solve this question, but they didn't tell me what K was. And I'll say, they don't need to tell you what K is because K never changes. K is a constant. It's on the back of your formula sheet, okay? And it's what we call the Coulomb's law constant. It's K, and it's 8.99 times 10 to the power of 9, okay? It's exactly like, remember the gravitational constant from physics 20? It's just a number, right? And it was the exact same idea in physics 20, right? The relationship, the actual relationship between the force of gravity and the masses of the object and how far apart they are was this. That's really the relationship, right? It depends on the mass and it depends how far apart they are. But if you just put in the numbers there, you're always off by this factor. So for the actual force in newtons. And so to correct for that, you just multiply by that proportionality constant, G, the gravitational constant, okay? And so it's almost like, the way I think of it is this is kind of like, you know, in a video game, you can go into like the settings sometimes and you can like mess around with like how strong this universe's gravity is or like how fast things move, right? You can kind of change the settings. These are almost like the settings for our universe, right? This number determines essentially how strong the force of gravity is, right? You can see if G had happened to be in our universe a larger number, the force of gravity would be a stronger force, right? And so this K, this is the constant that governs how strong the electric force is. Okay, so if K happened to be a bigger number, electrostatic forces would be stronger, right? It's one of those things where if you're asking me why is that K, all I can really say is, well, that's how our universe works, right? We've measured it, we've tested it, and to make it work with our human units, this is how big that proportionality constant is, right? That's just the way the universe works. Why isn't the K a bigger number? Because in our universe, the electrostatic force isn't stronger than this, right? Why isn't it a smaller number? Because we've measured it, and in our universe, the electric force is not weaker than what this number gives. It's the settings in the code that runs our universe, right? Okay. So now that we've talked about the relationships, right, what the electric force actually depends on, which is the charges of the two objects and how far apart they are, let's get to an actual equation. What does the electric force actually equal? Okay, and here it is. So the relationship that Coulomb found between the charges of the spheres, their separation distance, and the resulting force, which is now known as Coulomb's law. So from now on, if I refer to Coulomb's law, what I'm talking about is this equation here, okay? Fe equals kqq over r squared, okay? This is it. So notice that relationship part that we talked about is in there, right? It's directly proportional to the charges and inversely proportional to the distance between them squared. We just don't quite get the right actual force in newtons until we multiply it by this constant. Because again, that is how strong the electric force is, right? Right? Again, asking why isn't K a different number is a bit like asking why doesn't the earth pull me harder or less hard, right? The answer to that is just that, well, because it doesn't. We live in this universe and we can observe how hard it pulls you, right? If it pulled you harder, you could just ask the same question. Why doesn't it pull me weaker, right? So it's the same idea here. This is how strong the electrostatic force is. We know it depends on these things because when we vary them, it responds in this way. It's just that you don't get the right actual number for the force in newtons until you multiply it all by this multiplier. Again, it's the settings in like the operating system of the universe that K governs how strong the electrostatic force is. If it was a bigger number, they would repel each other more. If it was a smaller number, they wouldn't repel each other quite as hard, but based on our observations, they repel each other exactly hard enough where this is the right number for us to use. Okay, so just running through the variables here, notice absolute value. I'm in math brain mode. In physics, we would say that's the magnitude of the electric force, but it is a lot like absolute value from math class if you've taken your math 20, right? All it's saying is that this is only going to give us the size of the electric force. It's not going to give us what direction it's in, okay? We're going to have to think about direction here in these cases because we'll have to think about, all right, if it was a positive charge and a negative charge, which way would it be pulled, right? Or if it's a negative charge near another negative charge, which way would it be pushed? So this will never give us the direction of the electrostatic force, but it will give us the magnitude, how big it is. But it's not too bad to get the direction from just thinking about it, okay? So that's the magnitude of the electrostatic force between the two charged objects in newtons. Well, that makes sense. That's how we measure forces, in newtons. Q1 and Q2 are just the net charges of the two objects that we're calculating the force in between them, whether it's attraction or repulsion. We know that charges, Q, are measured in coulombs, symbol C, okay? R is the separation distance between the two charged objects in meters. Well, that makes sense. We measure distances in meters. And then K is the Coulomb's law constant, or the Coulomb constant for short. And it is 8.99 times 10 to the power of 9. And they're not giving us the units here because they want us to figure them out on our own. But we know how to do that, right? If we can figure out, based on this relationship, what K is equal to, well, then we can just put in the units for those quantities, and that will tell us what units Coulomb's constant must be in. So let's go ahead and do that. So starting from here, we want to solve for K so we can figure out what its units would be. Okay, it is definitely not by itself because it's being multiplied by Q and being divided by R squared. So we need to undo those operations. So let's first multiply both sides by R squared. That'll give us that R squared times the magnitude of the electrostatic force is equal to Coulomb's constant times the two charges. And now we want to solve for K, Coulomb's constant. It's being multiplied by these two charges. So let's go ahead and divide both sides by those two charges. And we end up with this. Coulomb's constant, K, is equal to the distance between the charges squared times the electrostatic force between them divided by the product of their charges, right? So if we're asked what are the units of the Coulomb's constant, K, well, we can now do this, right? Because we can say, all right, so K is going to be measured in, right? Well, it looks like it's a distance squared times a force divided by two charges multiplied together, right? So look, how do we measure distances? In meters. And then we're squaring those meters. So we're going to have meters squared times how do we measure forces in standard units? Newtons, right? It didn't say base units, so we can use newtons. We don't have to call them kilograms, meters per second squared, divided by two charges multiplied together. Well, charges are measured in coulombs, so the denominator has units of coulombs times coulombs, or coulombs squared. So this gives us that the units of Coulomb's constant, K, are going to be newtons times meters squared divided by Coulomb squared. So Newton meters squared per Coulomb squared. Newton meters squared per Coulomb squared. And if we check over here on the back of the formula sheet, okay, sure enough, Newton meters squared per Coulomb squared. And we can see that that actually makes a lot of sense because look, if this is measured in Newton meters squared per Coulomb squared, well then when I multiply it by coulombs and coulombs again, right, I had per Coulomb squared, but then I times by coulombs and times by coulombs, I no longer have per Coulomb squared, right? They've canceled out. The Coulomb squared here will cancel out with the Coulomb squared in the denominator of K's units. And then I'm taking Newton's meters squared, that's what's left, and dividing it by meters squared. So I'll just be left with newtons, right? So that's what I should get. If I take Newton meters squared per Coulomb squared, cancel them out with Coulomb squared, and then cancel out the meters squared, I'm left with newtons, which are the units of force. So it works out and it checks out. All right. All right, now very important. When you are using this Coulomb's law equation to calculate the electrostatic force or between the two charges, right? You do not use positive or negative with those charges, right? Remember, do those positives and negatives like actually mean anything really mathematically or in terms of like direction, right? Like a negative force is a vector, so we would think of a negative force as meaning, okay, that must be a force in the negative direction, right? But a positive charge, that doesn't mean it's like charged north or upward, right? A negative charge doesn't mean it's charged left or west or something like that, right? Those names, those positive and negative, are purely to convey that there are two types of charges and they're opposites. So we picked two words that mean opposite, right? Positive and negative. We could have just as easily called charges black and white or something like that, right? Something opposite, okay? And so it doesn't make any sense to put in a negative Q or a positive Q here because that's going to tell us that our force is negative, which would mean direction, but charge is not a vector. Charge is a scalar, right? It's just a property of something. The same way you have mass, that's just a property of objects, of matter, right? You also, or at least some things, have a charge, right? Protons just have a charge the same way they have a mass. Okay, it's a scalar. It's not talking about what direction is going on or anything like that. So all of that to say, we're not going to put in those positives and negatives when calculating with this equation. Okay, charge is a scalar. The signs don't mean anything about the direction of the force. And again, to get the direction of the force, we'll need to think about the situation. Okay, so we'll have to look and say, okay, which object are we thinking about? Is it being attracted or repelled? And if it's being attracted or repelled, which direction does that mean it's being pushed? That's how we'll get the direction of an electric force. Ready to try one out? So this one asks us, what is the electrostatic force felt between a proton and an electron 1 centimeter apart? So let's go ahead and just draw our diagram here. I'm going to take a proton, which we know is positive, symbol P plus, and an electron. Obviously, they don't actually look like little balls, but that's the way we can represent them. So an electron, symbol E minus, okay, and they are 1 centimeter apart. So there we go. There's a little diagram to represent. All right, I actually changed my mind about the colors there, but okay, so what do we know? Will they be attracted to each other or repelled? That's the first question we can ask ourselves. Well, they're going to be attracted, right? Opposites attract. A proton's positive, an electron is negative. So this is a mutual force of attraction. Really, it's Newton's third law going on in a way here, right? The electron is going to attract the proton, but for every force, there's an equal and opposite force. So when the electron pulls on the proton pulls back on the electron just as hard, right? And I mean, you can see that in the equation. It's not like this says the force on charge 1 or the force on charge 2, right? Either way, we would put the same two charges in. If I asked you to calculate the charge on the proton because of the electron, the two charges you would put into the equation would be the protons and the electrons. If I asked you to calculate the charge on the the force on the electron because of the proton, well, once again, the two charges you would put into the equation would be the protons and the electrons, right? So just like the force of gravity was, this is a mutually attractive or mutually repulsive force. So they are both feeling whatever force we're about to calculate, right? And that's actually what we're asked to find, the electrostatic force between them. Okay, if they had asked for the force on the proton, we wouldn't do anything differently. It's just we'd be able to actually say, it's towards the electron. Here, we're just going to have to say it's attractive. They're both attracted to each other. Okay, so we know their separation distance, that is r. Okay, that's r in our equation. And hey, we know the charge of a proton. You might be saying we do. Right? They didn't give it to us. No, but they don't have to because it is always given to us on the back of our formula sheet. The charge of a proton is plus 1e. And what's e? Well, I got good news for you. That's also given on the back of your formula sheet. The elementary charge is 1.6 times 10 to the negative 19 coulombs. The charge of an electron, same thing, but negative, right? The charge of an electron is negative 1e. So we've got our charges, we've got our separation distance, and we always have K. That is just Coulomb's constant, okay, which again is given on the back of your formula sheet. So we've got everything we need here, okay? We can just set up our equation, plug in, and solve. One thing we do need to be careful about though, do we measure distances in meters, right? Is Coulomb's constant set up to, we do measure distances in meters. What I meant to say was, do we measure distances in centimeters, right? Is Coulomb's constant set up to work with centimeters? No, right? The standard unit is meters. So we do need to convert that to meters. But we know that there are 100 centimeters in 1 meter, right? So we can go ahead and say, all right, well, 1 meter is the same as 100 centimeters. So it makes sense that we need to divide by 100, right? It takes 100 centimeters to make just 1 meter. So divide by 100 to figure out how many meters this is. And it's 0.01 meters. Just another reminder, if you're ever saying, oh, what did centi mean again? Was centi 1/1000th or was it 1/100th? It's on the back of your formula sheet, right? It's saying that centi is the same as 10 to the negative 2, right? 10 to the negative 2, well, that's just 1 over 10 to the positive 2, or 1 over 100, right? So a centimeter literally means 1/100th of a meter, okay? All right, let's actually go ahead and set up our equation and calculate. So we know the two charges, we know the distance between them, we can calculate the force, so it's going to be the electrostatic force between this proton and proton and electron is going to be K. All right, from the back of our formula sheet, K is 8.99 times 10 to the power of 9 Newton meters squared per Coulomb squared. Charge 1, doesn't matter what we call 1 and 2, let's say 1 is the proton. Remember, we're not going to put in any negatives here, so 1.6 times 10 to the negative 19 coulombs. The other charge happens to have the same charge here, so if we want, we could have just squared that, but I'll write it out to really show that it's Coulomb's constant times the charge of one object times the charge of the other object, divided by their separation distance squared. So divided by 0.01 meters squared. And when you put that all into your calculator, you're going to get 2.3 times 10 to the negative 24 newtons. Now it's a force, which is a vector, so we should be thinking about direction. However, here, right, it's actually, it depends who you ask, so to speak, which direction it is, right? If this is really how they were, I mean, it didn't tell us the proton was on the left and the electron was on the right, but like the proton feels a force of attraction in one direction. Because the electron's over here, it feels a force of attraction in the total opposite direction. So it didn't give us enough information to say what like specific direction this force is. And it's also in opposite directions depending on whether you ask the proton or if you ask the electron. So the best we can really do here for like a direction is just attraction. Or you could say towards one another if you wanted, but that's what attraction means. All right. Now, really quickly, since it might have been a while, I'm just going to do a quick calculator tutorial on entering stuff like this really quick, okay? Just because, you know, we're dealing with really big numbers and really small numbers, and this is where calculator mistakes can start to creep in. So I'll just show you how to deal with these really big and really small numbers in a calculator in the most convenient way. All right, so let's say we were trying to enter that exact one we just did. We want to put it in our calculator. The number one thing I see students do that I tell them they're making their lives way harder than it needs to be is this. So we wanted to do 8.99 times 10 to the power of 9. And what they'll do is they'll actually go times 10 to the power of 9, right? And there's nothing wrong with that, but that was a lot of buttons to press, and it's also way easier now to tell our calculator to do something that we don't actually mean, right? Because now you've introduced this other like operation, 8.99 times 10 to the power of 9. For example, like we're eventually, like if we were to divide this by some other exponential number, like, I don't know, 1.2 times 10 to the power of 3, this is where students often get a mistake because they'll go divided by 1.2 times 10 to the power of 3, and they think they're telling their calculator to divide 8.99 times 10 to the 9th power by 1.2 times 10 to the 3rd power. But they're actually not. They're telling their calculator to take 8.99, multiply it by 10 to the power of 9, and then divide it by 1.2. And then they're telling their calculator to take the result of that and multiply the whole thing by 10 to the power of 3, which is not what we want, right? We were trying to divide by this whole thing. So anyway, that's what I mean when doing it this way. Not only does it take more work and more button presses, it's also a lot easier to make a mistake in how you're entering it. So I'm going to strongly recommend that instead of doing that whole times 10 to the power of stuff, okay, make use of this button here that I'm highlighting in red right now, okay? So see those big E's? Those two big E's, uppercase E's, see how they're blue, right? That means if we press second and then them, it will give us that. Now, what that symbol means is literally times 10 to the power of, okay? And whatever we say next is, we know what we're telling our calculator to take it times 10 to the power of. That was a confusing sentence, right? I'll show you what I mean. Okay, so to enter the one we just did in the notes, we wanted to do 8.99 times 10 to the power of 9. So instead of going times 10 to the power of, I'm just going to go second E. Okay, and that means 8.99 times 10 to the power of, and we wanted to do times 10 to the power of 9. Okay, so that's what that means now. My calculator knows exactly what I mean, and it's not going to get confused. Okay, so that's K. We want to do KQQ. So times 1.6 times 10 to the power of negative 19. So once again, I want to multiply by 1.6 times 10 to the power of negative 19. So I'm just going to go E. That means times 10 to the power of, and then I'll just say negative 19. Okay, and then we wanted to do that again. It was times 1.6 times 10 to the power of negative 19. We wanted to do it twice. Okay, so there we go. That's KQQ. Honestly, at this point, I would probably just hit enter, get my answer. Now I've got that. I've got the numerator of our fraction, and we just wanted to divide it by r squared. So I can just take that answer and divide it by 0.01 squared. And that gives us this. So notice our calculator is telling us, see that E there, right? That's saying the answer is 2.30144 times 10 to the power of negative 24. So your calculator uses the E anyway to talk to you. You might as well get used to it and use it to talk to it as well, because it makes things way easier. And then it asks us, how does this compare to the gravitational force between them? So, I mean, a proton has mass, an electron has mass. So we know from physics 20, that means they do feel a force of gravity towards each other, right? Fg, the force of gravity between any two objects with mass, is g times their masses divided by r squared. So you might be saying, well, we don't know the mass of a proton or the mass of an electron. We actually do. They're also given on the back of a formula sheet, right? So interestingly, they actually don't have the same masses. An electron is about 1,800 times smaller than a proton. Electrons are tiny. We'll get into why that is later in the course. Okay, well, maybe not why that is, but what's interesting about that, I'll say. Okay, so the electron has a mass of 9.11 times 10 to the negative 31 kilograms. The proton has a mass of 1.67 times 10 to the negative 27 kilograms. And the gravitational constant that we need to calculate the force of gravity between any two objects with mass, right, big G, is 6.67 times 10 to the negative 11. So we've got big G, we always have that, right? We've got the mass of the electron, the mass of the proton, and the separation distance is 1 centimeter. So we've got everything we need to calculate the force of gravity between them. Let's see what happens when we do that. All right, so I've set up my equation there for calculating the force of gravity. Let's put in our numbers. G is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. That never changes. It's the gravitational constant. Mass of a proton and mass of an electron we can get from the back of our formula sheet. And they're separated by 1 centimeter. So putting that all into our calculator, this is a good chance for you to practice that, putting in those numbers. And I would encourage you to practice that, right? It's not one of those things you want to realize you don't know how to do on a test or the diploma, right? So maybe pause the video, try calculating this out, and see if you get the same thing as me, which was 1.0 times 10 to the negative 63 newtons. Now it's gravity. We know gravity is always attractive, so this would actually also be attraction. Okay, but something interesting has just kind of showed itself to us here, right? The electric force is much, 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 much stronger than the gravitational force, right? In fact, we're going to study in Physics 30, there are 4 forces, okay? And actually, those are the only 4 forces. We'll meet them along the way. Every other force that you've talked about is actually just one of these forces in disguise. So there's 4 fundamental forces. Up until now, you've met 2 of them. One is the force of gravity, and one is the electrostatic force, okay? Now, out of all 4 forces, by far, gravity is the weakest. Gravity is incredibly weak. Now, right now, you might be saying, wait, what? How can that be true? Because gravity is the force I notice the most. Like, that's the force that kind of dominates my life, right? I see gravity around me all the time, right? Well, that's because most things are electrically neutral, right? Like, why is gravity the thing that keeps the Earth going around the sun and not the electrostatic force if the electrostatic force is so strong, right? Well, because the Earth is overall neutral. It's got just as many protons as electrons, give or take. And same goes for the sun, right? But it does have lots of mass, so there's still that force of gravity kind of dominating, right? And you are observing the effects of the electrostatic force. The fact that you can't put your hand through the table, right, is a result of electrostatic attraction between the electrons and the protons in the atoms of the table and in your hand. And it's the electrons in your hand repelling the electrons in the table. So believe it or not, you do actually see the electrostatic force in action all around you. But I just want to point out here, right, times 10 to the negative 63. So that's 0.000000063 zeros, and then we finally hit a 1. Whereas this is 0.00, only 24 zeros until we hit a 2, right? So that means this is roughly 10 to the power of 30, 40, 10 to the power of 40 times weaker than this, right? 10 to the power of 40. That is a huge number. I don't even know what that number would be, but it's a 1 and then 40 zeros, right? That many times stronger. So the electrostatic force is much, much stronger than the gravitational force. So since it asked us to compare, I mean, one way we could compare is by saying they are both attractive. That's true. But we could also point out that the electrostatic force is, to figure out how many times bigger that is, we could just divide them. So 2.3 times 10 to the negative 24 newtons over 1.0 times 10 to the negative 63 newtons. That'll tell us the factor by which the electric force is bigger. And yeah, it's 2.3 times 10 to the 39 times stronger, right? That is a huge number, okay? Just for the sake of being dramatic. Look. There, I actually wrote it out just to let it sink in how much bigger it is, right? It's, I did some quick math. It's a roughly 2.3 thousand billion times stronger, okay? So, all of this to say, the gravitational force is much weaker than the electrostatic force, pound for pound, okay? It's actually, one of the interesting things is an ongoing question in physics research is, why is the gravitational force so weak compared to the other forces, right? It's one of those things that has led to, like, that's weird. Why did it come out so weak compared to the other ones? And it's an ongoing area of research. We're actually not sure. Okay, let's try this one out. So 2 objects feel an electrostatic force of repulsion of 100 newtons. So that's the force they feel, originally anyway. Fe for the electrostatic force. If their separation distance were tripled, so we're going to move them to be 3 times further away. So what variable are we changing from our equation? The r, right? Their separation distance. What we're doing is we're taking r and we're turning it into 3 times whatever it originally was, right? We're turning r into 3r. And now we want to know, what is the new force? Okay, well, this just relies on the fact that this is an inverse square relationship, right? The electrostatic force is equal to KQQ over r squared. So we can see, right, it's an inverse relationship. Making this bigger is going to make this smaller because we're dividing by a bigger number. But not only are we dividing by a bigger number, we're dividing by that bigger number after it got squared. Okay, so just to explore this a bit, let's just make a table of values. Okay, so just to get a feeling for this inverse square idea, it's been a while since Physics 20, I get it, okay? So what I'm going to say here is we're just going to change the distance between the two objects, right? We'll have them 1 meter apart, then 2 meters apart, then 3 meters apart, then half a meter apart, and a third of a meter apart. And we want to think about what that means for 1 over the distance squared, and therefore what it means for the force between them. Right? Because as our equation shows us, the electrostatic force is inversely proportional to the distance squared, right? Another way to rewrite this equation would be you could just write it as KQQ times 1 over r squared. And that makes it a little more obvious that, okay, yeah, whatever happens to not r, not 1 over r, but 1 over r squared is going to be the factor by which the electrostatic force changes. Okay, so let's start out here. When r is 1 meter, well then 1 over r squared is just 1 over 1 squared, right? Which is just 1 over 1, which is 1, okay? But now what if we moved our charged objects further apart? In fact, let's move them from 1 meter apart to 2 meters apart. So we are doubling the distance between them, okay? So for 1 over r squared, our r has gone from being 1 meter to 2 meters. So we've made the distance 2 times bigger. So that means, though, that we now have 1 over r squared is 1 over 2 squared, which gives us not 1/2, but 1/4, right? So doubling the distance made 1 over r squared 1/4 as large as it used to be, right? It used to be 1, now it's 1/4. So what happened to our electrostatic force when we doubled the distance between the two charged objects? It didn't get half as big, it got 1/4 as large, right? Or 4 times smaller, making r 2 times bigger, made the electrostatic force 4 times smaller, or 2 squared. Let's keep going. What if we now think about making them 3 times further apart than they started? So going from the two charged objects are 1 meter apart to now they're 3 meters apart. Well, if r has become 3, then 1 over r squared, right? We've now got 1 over 3 squared. So 1 over r squared didn't become 1/3 as large, it became 1/9 as large, right? And same goes for the electrostatic force, since that really just depends on 1 over r squared, right? So moving them 3 times further away made the force 9 times weaker, right? 1/9 the force from triple the distance. Okay, what if we move them closer? So now we go from a distance of 1 meter to a distance of half a meter. In other words, we multiply the distance by 1/2, or you could say we divide the distance by 2. Well, let's think about that for 1 over r squared. We've got our r is now half a meter. They're half a meter apart, so 1 over 1/2 meter being squared. Well, that's 1 over 1/2 squared is 1/4. And dividing by 1/4 is the same as multiplying by 4 over 1, right? Dividing by a fraction is the same as multiplying by its reciprocal. So we went from a 1 over r squared of 1 to a 1 over r squared of 4. So it got 4 times larger. Look at that. Making the distance 2 times smaller made the force 4 times larger. Do you see the inverse and the square at play there, right? Inverse in that when this goes up, when this gets larger, this gets smaller, right? And the square is showing us that it changes by a factor of however this changed squared, right? 2 squared is 4. So this got 2 times smaller, it got divided by 2. That made this get 4 times larger. It got multiplied by 4. Dividing by 2, multiplied by 4. The same way here, multiplying by 2, divided this by 4. right? Last one. I want you to make a prediction before I do it. When we make the distance 3 times smaller, so we divide the distance by 3, we go from 1 meter apart to 1/3 of a meter apart. What do you think's going to happen to the force? 2 parts to your answer. Will it get bigger or will it get smaller? And by what factor? Ready? So, dividing our distance by 3, moving them so they're 1/3 of a meter apart instead of 1 meter apart. Well, 1 over r squared then is going to be 1 over 1/3 squared. 1/3 squared is 1/9. And 1 divided by 1 over 9 is the same as 1 times 9 over 1, or 9. So look at this. Making this 3 times smaller made this 9 times larger, right? So inverse, whatever happened to this one when it got smaller, this one got larger, and square, because this was divided by 3, this was multiplied by 3 squared, 9, right? So this is what we mean by an inverse square relationship. Doubling the distance is not going to cut the force in half. It's actually going to cut it by 1/4. Okay, and it's all because of that squared in the denominator. So with all of that being said, right, let's just take a look at this one. Their separation distance were tripled. What is the new force? So R got 3 times larger. We know that that means the electrostatic force should get, first part of your answer, should it get smaller or bigger? If we move them 3 times further away, we made the distance 3 times larger. The force should get smaller, that's right. And now, okay, by what factor should it get smaller? What are we going to multiply the force by if we made the distance 3 times bigger? Is it 1/3? No, it's going to be 1/9, right? So our answer is just going to be 100 times 1/9, or 100 divided by 9. Multiplying R by 3 results in the force getting divided by 3 squared, right? Divided by 9. Just to show you here with another way of looking at it, right? If originally the electrostatic force was 100 newtons, the distance, we're just going to say, we don't know what it is, but we'll just call it R, and the electrostatic force should be KQQ over that R squared. Well, now we want to know what the new force is. We sometimes use this little prime, it looks like an apostrophe, just to say what's the new one, right? That's what we're trying to figure out. And R, our new R, is just, we don't know what it is, but we know it's 3 times the original separation distance, R, right? And what's the new force? Well, it's K times Q over the new R squared, right? Fe is KQQ over R squared. But we know that the new R is just 3 times the original R. So we can just say, okay, the new electrostatic force is going to be K times Q over, yes, the new R squared, but the new R is just 3 times the original R, and we're squaring that new R, right? And you can see here already where this might be headed, because look, this now, what happens when you square 3R? You don't get 3R squared, you get 9R squared, right? This is 3R times itself. 3 times 3 is 9. So we now have introduced a factor of 9 into this denominator, because we were tripling that R, but that R gets squared, right? So look, we didn't take the original force and divide it by 3. We took the original force and divided it by 3 squared, or 9, right? To really drive the point home, look, what's this? What's KQQ over the original R squared? Well, it's just the original electrostatic force. So what we're literally saying here is that the new electrostatic force is the original electrostatic force divided by 9, right? Or if you really want to show it, it's 1/9 times our original electrostatic force. 1/9 times Fe, or Fe over 9, right? So that means it's 1/9 times the original force of 100 newtons, which comes out to be 11.1 newtons to 3 significant digits. Okay, so that's all the inverse square relationship is. Sometimes I find students really overthink it, but all it's saying is that, again, inverse, whatever happens to R, if it gets bigger or smaller, the opposite will happen to the electrostatic force. You don't even have to memorize that. First of all, the equation shows us, right? We're dividing by R to get Fe. So if I make it bigger, this is going to get smaller, right? That's the first clue, okay? Also, just think about it, right? What would make the force between two objects get stronger? Do you think it's when you move them further from each other or closer to each other, right? Decreasing the distance between them should make the force get larger. Increasing the distance between them should make the force get smaller. That's the inverse part. And the square part is just from the fact that we're not actually dividing by R, we're dividing by R squared, okay? So making R 3 times bigger will make the electrostatic force 9 times smaller, or 1/9 as large. Making R, 5 times smaller will make the electrostatic force 25 times larger. Inverse square relationship. Okay, so let's try this one. Two objects with identical charge magnitudes. Okay, so meaning they have the exact same charge. We don't know what it is, but they have the same charge. Are held 15 nanometers. That little n means nano. If we check the formula sheet, you can see that nano means 1/1,000,000th, or 10 to the negative 9. Okay, nano, lowercase n. So that literally means this one here, 15 nanometers, that's 15 times 10 to the negative 9 meters. Okay, or if you like, 1.5 times 10 to the negative 8. Okay, and feel an attractive electric force of 70 millinewtons. So the force they're feeling, Fe, is 70. Milli, from the back of your formula sheet, or you might just know this one, is 1/1000th, or 10 to the negative 3 newtons. So there's our electrostatic force. There's the distance they're held apart. We're being asked in A, what are the magnitudes of the charges? So we want to figure out the charges. Okay, well, we know that for two charges, being held apart at a certain distance, R, just drew the picture to represent this here, right? We can calculate the electrostatic force between them, attractive or repulsive, of what force they're feeling because of each other with KQQ over R squared, right? Well, we were given Fe, we were given the force between them. We always have K, that's a constant, 8.99 times 10 to the 9, and we were given the distance between them, R. But it kind of looks like at first we have two unknowns, don't we? Except the two charges, their two charge magnitudes, the two Q's, are identical. So what does that mean? It means Q1 equals Q2. So multiplying them here together is really just multiplying the same number by itself. So let's just call it Q, right? Q1 is the same number as Q2. Let's just call it Q. And then Q1 times Q2 is just Q times Q. It's Q squared, right? We'll just get, since it's the same charge magnitude, we can figure out what it must be, right? It's just the same number times itself. That wouldn't work out if they were two different numbers. We really would have two things we didn't know. But in this case, there's only one thing we don't know. It's just being multiplied by itself. So we can rewrite this then as the electrostatic force is just equal to K times Q squared, right? Q times Q, it's the same number, over R squared. And now we just need to solve this for Q. It's the only thing we don't know. So let's multiply both sides by R squared. Okay, that'll give us this. We're solving for Q, remember, reverse order of operations, so we had to deal with multiplications and divisions before we can deal with the exponent, the fact that it's being squared. Okay, but now it's being multiplied by K. Well, we can undo that by dividing both sides by K. And we're almost there. We get that Q squared is equal to R squared times the magnitude of the electrostatic force between them divided by Coulomb's constant, K. And we're almost there, but we didn't want to solve for Q squared. We wanted to solve for Q. So we just need to, what's the opposite of squaring? It's square rooting. So whatever this charge is, it's going to be the square root of the distance between them squared times the electrostatic force between them divided by Coulomb's constant. Okay, so let's go ahead and plug in our numbers because we have all that stuff. All right, and then All we got to do is carefully enter this into our calculator, right? I would definitely not try to enter this all in one big step. Break it up into smaller pieces, right? Do 15e negative 9 and square it. Then multiply that by 70e negative 3. Then divide by 8.99e9. Hit enter, right? And then take the square root of whatever you get. Don't be scared to like hit enter, even write down your answer as you go. But when I did all that, I got 4.1856 times 10 to the negative 14. Now we're expecting units of coulombs out because this is charge, right? But let's maybe do a unit check. That's a valuable skill just to make sure what we set up here really does give us units of coulombs. So what have we got? We've got an r squared, right? So I use square brackets. That's kind of the universal sign for I'm just talking about the units right now. So meters being squared times the electrostatic force, which is measured, it's a force, so it's measured in newtons, divided by Coulomb's constant, which from the back of your formula sheet, if you're not sure, it's newtons times meters squared per Coulomb squared. And then that's all being square rooted. And what we want to know is, does that actually give us units of charge, right? Does it give us coulombs? Well, let's see. First thing I would do to kind of simplify here probably is, honestly, we're dividing by this fraction. So let's multiply by its reciprocal because that's always easier to think about. So instead of dividing by Newton meters squared per Coulomb squared, let's rethink of that as multiplying this by Coulomb squared per Newton meter squared. That'll give us this, right? We're dividing by this fraction, so it's the same as multiplying by its reciprocal. So it's the same as taking this, multiplying it by Coulomb squared, and dividing by Newton meters squared. And then look at this. We're on our way. This looks pretty promising because meters squared over meters squared cancels out. Newtons over newtons cancel out. And we're left with the square root of coulombs being squared. And the square root of coulombs squared is coulombs. So that's our unit analysis there, and it checks out. We were hoping to be able to be calculating a charge right now, right? And sure enough, we got units of charge out. So if nothing else, we feel pretty good about our manipulation, right? We know we did something right because we're getting the correct units out. Okay, so all that's left to do though is I was only given 2 significant digits. So for my final answer here, I should state it to 2 significant digits. So 4 point, careful, not 1, right? That 1 is followed by an 8, so it's closer to 4.2 times 10 to the negative 14 coulombs. Now B asks us how many excess electrons are present in the negative charge, right? Well, we now know what its total charge is, right? Each of them has this as its charge. And remember from the previous lesson, every excess electron, I mean, we know the charge of an electron. So again, it's that thing of protons and electrons just cancel each other out, right? These have a charge of positive 1.6 times 10 to the negative 19 coulombs. These have a charge of negative 1.6 times 10 to the negative 19 coulombs. So overall, this object would be neutral. How it gets a charge is by having more electrons than protons, right? And for every one more electron it has another charge of negative 1.6 times 10 to the negative 19 coulombs, right? Right now, these would all be canceling out, and its net charge would just be the charge of that one electron, negative 1.6 times 10 to the negative 19 coulombs. If it had 2 extra electrons, it would have twice as much charge. 2 times 1.6 times 10 to the negative 19 coulombs. If it had 3 extra electrons compared to protons, right? 3 times that elementary charge. So every extra electron contributes 1.6 times 10 to the negative 19 coulombs of charge. So this is the situation we've really got, right? The charge per excess electron is this. That's for every 1 extra electron, you get this much charge. And we know that the total net charge this thing ended up having was this much. Notice using my unrounded answer because we don't want to over-round and be off in the end, okay? So if every electron contributes this much and we ended up with this much total, how can we figure out how many electrons that would take? Right? Really, what we're saying is how many times does this go into this, right? We just need to divide them. How many of these would it take to make a total charge of this? So by dividing them, we can find the number of electrons. Okay. Okay, so our total charge, 4.1856 times 10 to the negative 14 coulombs over the charge that each electron contributes, 1.6 times 10 to the negative 19 coulombs. Not going to include the negative there, right? I mean, because this is a scalar thing we're talking about here, and we're just trying to figure out how many of these to get this. Or you could think of it as they're ultimately both negative, because the net charge would be negative if it has extra electrons. And so we got that the number of electrons it would have to have is, I got 261,600. Now I misspoke there. I said that's the number of electrons it has. We know that's not true, right? That's the number of extra electrons it has compared to protons. It probably has billions more electrons than that, right? But this is how many more electrons it has than protons. Of course, that's way too many significant digits. We do not have that level of precision based on what we were given. We only get 2 sig digs worth of precision, so it should be 2.6 times 10 to the power of 1, 2, 3, 4, 5, 2.6 times 10 to the 5th power extra electrons. And there we go. All right, so go ahead and give this one a try, right? You're told about in an hydrogen atom, an electron is this far from a proton. Okay, so you know on your formula sheet, you can get the charge of each of those. You have how far away they are, right? And you also have Coulomb's constant on your formula sheet. So it wants you to use that information to calculate the electrostatic force of attraction between the two charges. And then once you've done that one, feel free to pause the video, take a break from my voice, try a few more, right? You've got a lot of the skills you need for this lesson already, believe it or not. It's mostly that equation. We're just going to look at applying it in some different ways. So don't think you just have to do that one, but at the very least, try that one while it's fresh in your brain. And I do invite you to try a few more, get the hang of it, and then we'll continue on to looking at graphing and Coulomb's law. All right, so just a reminder here, when talking about, graphs in general and sketching graphs, it's a general skill. It's not specific to any equation, right? It's not like you're supposed to memorize what the graph looks like for a certain equation with certain variables, right? All any graph does is show us how y depends on x, right? When x changes, what's going to happen to y? Putting different variables there just means x represents something and y represents something else, right? So when we're dealing with a new equation, the equation can tell us that, right? If this is electrostatic force as a function of charge, we know that as charge gets larger, so does electrostatic force, that kind of thing, right? What we're doing here is understanding the relationships between the variables based on the equations, right? Even if you didn't know what any of this stuff meant, the equation tells you how the electrostatic force depends on the charge or on the distance they're separated by, right? So even if you had no idea what any of those meant, you could still sketch the graph of the electrostatic force as a function of the product of the charges, for example, right? Because you can see, okay, when these are 0, this will be 0, right? So that gives you the x and y intercept. When the charge is 0, the electrostatic force would be 0, right? And then you can see, okay, what happens to the force as the charge gets larger? Well, it would get larger too, right? If I have a bigger number here in my numerator, I get a bigger force as an answer as a result. So as we go this way on the x-axis, we're expecting to also go up on the y-axis. As x increases, so will y. And then we can just ask ourselves, and how does that happen, right? Is there any squaring or square rooting going on with the charges? No, right? So doubling QQ, putting a 2 up here, is also just going to double the charge. Or sorry, double the force, right? And so we can say, okay, so it's a linear direct graph. Doubling this will also double this, right? Tripling it will triple this. It's a linear relationship. So that's the broad idea. What I'm getting at there is that it's not about the specifics of the equation and what the variables represent. I mean, it is, but the graph is just showing us what we already know from the equation visually. It's showing us how one variable depends on another. And that's the thought process you should go through when sketching a graph. right? So just go through that thought process. Think about what's being manipulated and what's responding to that change, right? In this example, we were thinking about different charges and how the force would respond in response to that, right? If we increased the charge, what would happen to the force as a result? Then pick the equation, right? You'll have an equation on the y-axis, an equation on the x-axis. A variable on the y-axis and a variable on the x-axis. What equation from your formula sheet actually relates those? It's helpful to solve it for the responding variable, right? Because then you can actually look at the equation and see, okay, like we did here, right? If this is solved for the responding variable of the electric force, we can see, all right, so what would happen if I made this bigger, right? Or if I made it smaller, what would happen to this? Isolating it for the responding variable just makes seeing that easier. And then ask yourself those questions that we just asked ourselves, right? Where does the graph start? Meaning, like when x, our manipulated variable, is very small, what will y be? Will it be very big? Will it be 0, right? Will it be very small? What will y be when x is very small? Does it then, from there, like as x increases, what happens to y? Just like we asked ourselves here. As the charge gets bigger, the electrostatic force should get bigger. I'm not guessing. I don't have that memorized. I'm using the equation to tell me, right? If it does rise or fall, how does it do it? Is it linear or curved, right? When you double one, does the other double? Or when you double one, does it get multiplied by 4 or divided by 4 or something like that because of a squaring or a square root that's happening, right? If it's not linear, what's the shape of the curve? Is it getting bigger faster and faster and faster, or slower and slower and slower, right? And do the intercepts, or it not having intercepts, which is possible, do those make sense? Does it make sense for these variables and for this equation for it to not have intercepts at all, or for it to have the intercepts that it does, right? Does your x-intercept make sense? In this case, I think it does, right? We found that when the charge is 0, there will be no electrostatic force. That's all that's saying. When x is 0, y will be 0, right? Well, that checks out. If something's not charged, it doesn't feel an electrostatic force. And that's the thought process, right? You're just kind of going through and thinking about what's the relationship between the variable on my y-axis and the variable on my x-axis. So let's try this one out here. So an electron is released near a positively charged sphere. Great. They want us to sketch a graph to show the relationship between the magnitude of the electrostatic force and their separation distance. So that's what we would typically call r, right? So it's saying, how does the electrostatic force depend on how far apart these objects are? So first things first, what equation kind of governs this, right? What equation relates these two things? Well, there's only one equation for this, right? It's Coulomb's law, okay? And so what's our responding variable? What's our manipulated variable? That can be kind of tough to think about sometimes, right? But I mean here, what makes more sense? That we would change how far apart they are and the force that's acting on them would change because of that? Or that we would change the force that's acting on them and how far apart they were would change because of that, right? This is kind of the result of changing this, right? The forces depends on how far apart they are. How far apart they are doesn't depend on the force they're feeling, right? The reason they're feeling that force is, well, partially at least, because of how close together or how far apart they are. So I think our responding variable should be the electrostatic force, and that always goes on the y-axis, responding on the y-axis. And our manipulated variable is how far apart they are, our independent variable, and that always goes on the x-axis. Okay. So now let's run through our questions, right? What we're trying to look at is how does the electric force depend on how far apart they are, okay? So the equation is going to guide us. Again, note that you could do all of this without having any idea what this equation means, right? I mean, we should know what this equation means because we're in Physics 30 and this is part of the set of equations we have to use, okay? But for sketching this graph, the equation tells us, without us knowing what any of these variables even mean, it shows us how Fe depends on R. So let's go through those questions. When R is very, very, very small, right, even like 0, although it can't be 0 because then we'd be dividing by 0, which is undefined. And that makes sense physically too, since they can't be a distance of 0 from each other. That would mean they were right in the same spot, which can't happen, right? But, okay, so when r is tiny, when r is very, very small, to calculate FE, we'd then be dividing by a very, very small number, right? If we divide by a very small number, we get a very large answer, right? So when r is very, very small, when x is very small, close to 0, FE is very, very large. So our graph starts when r is tiny, FE is very large. So there's our starting point. Now from here, we've got to think about what happens as r gets larger. Again, the equation tells us. No guessing involved here, no memorization. Let the equation tell you. So what's going to happen to FE as r gets larger? As we increase on the x-axis, what's going to happen to the electric force? Well, I'm dividing by a bigger and bigger and bigger and bigger number, right? So the electrostatic force is going to get smaller and smaller and smaller. So we know we're headed this way generally on the graph. As x gets bigger, y needs to get smaller. Now, this is an inverse relationship, so it's going to follow that inverse shape. It's also an inverse square relationship, so be careful. It's not this, right? That would suggest that if we double r, right, maybe we cut FE in half, but that's not really what's going to happen here. We're going to have this inverse square shape, right? And again, any inverse graph is not going to be straight because, again, that fact that when x is very small, when the change in x is very small at the small values of x, we get a huge change in y. But up here, the same change in x leads to a much smaller change in y. Just goes back to that, table I showed in chapter 9, lesson 1, okay, where if y is 1 over x, then at first, very small changes in x can lead to huge changes in y, right? From 0.001 to 0.01 is only a change of 0.009, but since 1 over 0.001 is 1,000 and 1 over 0.01 is 100, it's a change in y of 900. Right? And then from 0.01 to 0.1, we get a change in y of 90, because 1 over 0.01 is 100 and 1 over 0.1 is 10, right? And then it's flipped up here for the large x's, a change in x from 100 to 1,000. Well, that's a change of 900. And then here, it's only a change of 0.009, right? To go from 1 over 100 to 1 over 1,000. So even without that square there, that is the shape of an inverse graph, but it's even more dramatic when we have an inverse square relationship. All right, and the last thing to think about here is just, does the shape of our graph, the intercepts or lack thereof, does it make sense? So we can see this doesn't have any intercepts. In fact, we can kind of see it looks like it has asymptotes. You might know that word from math. It's okay if you don't, but an asymptote is just a line that it seems to be approaching but not actually reaching, right? So it looks like it's approaching the electrostatic force on the y-axis being 0, but it doesn't look like it's reaching it, right? Now, does that make sense based on the equation? If we made r 1 billion, would the electrostatic force be 0? No, right? It would be tiny. It would be a very small number, but it wouldn't be 0. There's no number so big that we could divide by and actually get an answer of 0. So this kind of checks out, right? In fact, that's true. The electrostatic force does have infinite range. So even if two electrons are on opposite sides of the universe, they are ever so slightly exerting a repulsive force on each other, okay? And then on the flip side of that, we already talked about it, but it looks like x doesn't reach 0 either, right? R doesn't reach 0. And that makes sense because, well, they can't have a distance of 0. They can't be right on top of each other, right? They can't literally be in the same place. And so the electrostatic force shoots up to infinity as R gets closer and closer to 0, but doesn't reach it. Okay, so I'd say that graph looks pretty good. That feels like a pretty good relationship here. Now, one of the most common questions I get from students when I show this example here is they say, but hang on a second, the electron was near a positively charged sphere, so shouldn't they be attracted to each other? Shouldn't they be getting closer? And then shouldn't that mean that since they're getting closer, the force is getting stronger, right? And what that student, I like where their head is at thinking about that stuff, right? But be careful. what's on our x-axis? It's distance, right? So going this way, no matter what, it means we're thinking about making the distance larger, right? The x-axis, what the student is thinking of here, they're thinking of a force as a function of time graph, right? They're reading too much into like the story here, right? They're saying, well, they'll get closer. True, but what we're showing here on the x-axis is how far apart they are, the force they feel as a function of their separation distance, right? Not the force they feel as a function of how long it's been, because they're right. As time goes on in this actual situation, they'll get closer together, right? So that is a common student mistake because they're thinking of this as a force as a function of time graph. Even though they know they're supposed to make a force as a function of distance graph, they're forgetting that once they put distance on the x-axis, then that means going this way is thinking about the distance getting larger, and going this way is thinking about the distance getting smaller. Regardless of whether or not this electron is moving towards or away, we're thinking of how would the force depend on how close or far it was. That leads us into this next question here, which is, would the graph above look different if the sphere had been negatively charged instead? So if instead of releasing the electron by a positively charged sphere, we had released it by a negatively charged sphere. So this situation versus this situation. Take a second and think about it. Would the graph look different? Would the electric force depend on the distance they're separated any differently? Right? And the answer is no, it wouldn't, right? Sure, in this case, that electrostatic force would be repulsive. And in this case, it would be attractive, right? But it doesn't change the fact that the equation to calculate both is kqqq over r squared. And if we move this closer, the force will be stronger. If we move this closer, the force will be stronger. If we move this further, the force will be weaker. If we move this further, the force will be weaker. It's just that in this case, that force is attractive, and in this case, that force is repulsive. And since we're not worried about signs here, we're just talking about the magnitude of the electrostatic force, right? That doesn't change anything. An electrostatic attractive force gets stronger when r gets smaller, and it gets weaker when r gets larger, right? And the same goes for an electrostatic repulsive force, right? If this gets larger, we're dividing by a bigger number, so that gets smaller. It's just that now the force is repulsive instead of attractive. But it doesn't change anything about the relationship between the magnitude of the electrostatic force and how far apart the two charges are. It just changes whether that force is attractive or repulsive. Okay, so just a summary of what we said there, right? It would still look the same. Either way, that's the equation to calculate the electrostatic force, and we use that whether the force is attractive or repulsive, right? So the relationship between Fe and R is the same, okay? All right, now let's get into kind of a new skill. Touch on it in Physics 20 a little bit, but really gonna use it here in Physics 30 now. So these sketches, and that's what they are, they're sketches, right? Obviously we didn't actually plot any data or calculate anything with that. It was just getting a feeling for the relationships, right? Visually representing how Fe depended on R. So what if we actually wanted to perform graphical analysis though? Right? We know for graphical analysis, we always need a slope, an area, or an intercept, right? The equation tells us which one. If we're dividing y by x, slope. If we're multiplying y by x, area. If we care about the value of 1 when the other is 0, intercept. Or sometimes in some rarer cases, if we just want to know the value of x at a certain y or y at a certain x, we can read off the line of best fit. Now, all of those, right? What is the slope of this line? Well, that's not a very good question, is it? Because it has many different slopes. The slope up here is very steep, somewhere in the middle here, and the slope is very not steep here, right? So this doesn't have a slope. It has many different slopes depending on where you look. What about the area, right? I mean, you haven't learned calculus yet, so you can't really calculate the area of this shape, right? You would need to use integral calculus to do so. But you could calculate the area of like a triangle or a rectangle or something, but not this shape, right? Okay, all of these require slope, area, intercept. They require a best fit line, not a curve like this. And this is where the skill of graph straightening comes in. And it's really what it sounds like. It's about taking a curved graph like this and straightening it out into a linear relationship. Because for a line, we can calculate the slope all day long, right? Or we can find the area under a linear graph, right? That's easy. It's just triangles and rectangles, or we can find its intercepts, okay? So there is something we can do to straighten this graph and make it so that this nonlinear relationship, we kind of reconceptualize it in terms of a linear relationship. It's kind of fun. It gets your brain thinking in a neat way. So what does graph straightening actually entail? Okay, well, it requires you to use the equation to come up with another way of plotting the variables that results in a linear relationship between what is on the y-axis and what is on the x-axis. So it comes down to, I always tell students when trying to straighten a graph, first, just write out the relationship between the y variable and the x variable. And then that will actually, if not directly tell you, get you very close to being able to see how to make it linear. So it asks us, what would you need to plot in order to straighten the electrostatic force as a function of separation distance graph? So in other words, Fe as a function of R graph. Well, that's the graph we just made. And we know it's no good for graphical analysis, right? It's no good for graphical analysis because it's not a straight line. So we can't find the slope, the area, or the intercept. That's a sad face because we can't do graphical analysis. So, like I said, start by writing out the relationship. Start from the equation. So the equation is this. The electrostatic force is equal to KQQ over R squared. Now let's pull out of that the relationship between, like, the parts of this equation that tell us about how the electrostatic force depends on R, the separation distance, right? Well, we've seen and we know that it's just this, right? Yes, it depends on Q and Q, but if we're just focusing in on how it depends on R, it's this, right? It's inversely proportional to the square of R. Now, writing out this relationship actually tells us exactly what we need to do to straighten the graph. Because we're saying two things here. Yes, we're saying that the electrostatic force is inversely proportional to R squared, meaning that Fe as a function of R would give us this inverse square graph. But notice, we're actually kind of saying something else. We're saying that the electrostatic force is directly and linearly proportional to 1 over R squared. Right? I know that's a little bit weird to think about, but look, right? If I double 1 over R squared, meaning, I just multiply, I take 1 over R squared and I multiply it by 2, I double the electrostatic force. If I take 1 over R squared and I multiply it by 1/2, I multiply the electrostatic force by 1/2. And so that's the key there. Thinking about what we could put on our y and our x axis. Because remember, R is just a measurement. It's just a number. We could take it, square it, and then do 1 over that number and make those the numbers we put on our x axis, right? So what I mean is this. Instead of graphing Fe as a function of R, what if we graphed Fe as a function of 1 over R squared? And let's just say it looked like this. I kind of made up the numbers, right? Instead of plotting on our x-axis these R values, we're going to take those R values, do 1 over them squared, right? So 1 over 1 squared is 1, but then 1 over 2 squared is 0.25. 1 over 9 is 0.1111. 1 over 16, 1 over 4 squared, right, is 0.0625. We're going to make this what we put on our x-axis and then plot the force on the y-axis. And you can even see, all I did here was just pick a starting number and said, okay, so 100, if I doubled the distance, would become 1/4 as large, right? If I divided it by 3 squared, I'd get 11.1. And you can even already see that. Look, there's a linear relationship, right? 1 becoming 0.25 on our x-axis would go from 100 to 25 on our y-axis. And then 0.25 to 0.111 would go from 25 to 11.111. So we would get a linear relationship. And all it came from was, again, writing down the relationship between what's on our unstraightened y and x axes and looking at that relationship and seeing how it's also telling us about a direct linear relationship that we could plot, right? So instead of doing FE as a function of r, we'll do FE as a function of 1 over r squared. Let's try it out with another equation, just to get the hang of like this graph straightening thought process. So it asks us to try straightening the graph for period as a function of the length of a pendulum from Physics 20, okay? Now, I know it's been a while anyway, you might not remember this equation. I'll go ahead and throw it down for you here, right? What the actual variables mean and what we're calculating isn't what we're focused on right now, right? We're thinking about the relationships and what the equations suggest. That's actually why I picked an equation that you might not remember that well, so that you can see that it doesn't actually matter. The equation shows us what we're thinking about, how t is related to the length of the pendulum. T is the period, okay? So it's saying, how could you straighten this graph? T, period, as a function of the length of the pendulum. Well, first, let's just look at the relationship between t and L. Yes, it depends on the acceleration due to gravity, but how does it also depends on the length. So we want to know, what is just that dependence? Well, we can see that the period depends on not just L, right, but the square root of L, okay? That's how it depends on the length of the pendulum. So that is not going to give us a straight graph. It's going to give us a graph like this, right? It gives us a square root graph, y equals the square root of x type shape, right? And that's just because what the relationship shows us. As x increases by some factor, y isn't increasing by that same factor. It's increasing by that factor squared, right? Square rooted. So for example, when L increases by 4, t is going to increase by the square root of that, 2, right? But then when L increases by like 9, which is much bigger than 4, right? T isn't going to increase by a much bigger amount. It's actually only going to increase by 3 instead of by 2, right? Square root of 9 is 3. Square root of 4 is 2. So that's why we get that not straight curve. For every change in x, we're not getting the same factor change in y, okay? So, but here's the thing we need to do, right? We wrote down the relationship, and it shows us that we would not get a straight graph here. Oh no. Right? But at the same time, it's kind of telling us how to get a straight graph. Yes, the period is proportional to the length of the pendulum, the square root of the length of the pendulum, right? But that means it's directly and linearly proportional to the square root of the pendulum, right? So if we put L on the x-axis, we're going to get this curved graph. But instead of that, what if we put, right? Look at what this is telling us to do to get a straight graph. Put period on the y-axis, and instead of just putting the length of the pendulum on the x-axis, put the square root of the length on the x-axis. And that will give you a straight line, right? And now, when this increases by some factor, it's already been square rooted, and our period will increase by the same factor, giving us that straight linear relationship. There's actually another way we could have done this too, which would actually be to just square both sides, right? And then same idea. Okay, so this equation is now showing me that the period squared is proportional to the length of the pendulum, right? Now, if I just plot t as a function of L, I'm going to get that same shape. But it's showing me that, okay, what if on our y-axis we didn't put the period, but the period squared? Well, then this shows me that they are linearly proportional. Doubling the period squared can only happen if I double the length. So that's another way to get a linear direct relationship, right? It's kind of thinking outside the box a little bit. It's saying, okay, yes, this shows me that if I double the length, I only multiply t by root 2, for example, right? But at the same time, it's showing me that if I double, not L, but square root L, I would double the period, right? And that's how we arrived at this idea here. Instead of putting length on the x-axis, let's put the square root of the length on the x-axis. And notice, none of that required any super in-depth physics knowledge. It required me to look at the equation, pick out the relationship between the y and x axis. That's what I was doing here, right? That's the relationship between those two variables. And then let that tell me how to get a straight line graph. Cool, right? Let's try one from a diploma where we need to apply this skill. All right, so it tells us that an experiment is performed to determine Coulomb's constant, K. The experimental apparatus is illustrated below. Okay, so we've got a Van de Graaff generator. These are one of those like big kind of metal balls, and there's a belt inside that generates a lot of charge by friction, and then those electrons that kind of sit on the surface of it. You might have seen them at like the TELUS World of Science. You touch them, they make your hair stand up, all that fun stuff. Okay, so it tells us that the charge on the dome of the Van de Graaff generator is -2 times 10 to the -6 coulombs, and the charge on the graphite-coated pith ball is -3 times 10 to the -8 coulombs. So telling us it's graphite, meaning it's conductive. Okay, so as the separation distance, d, between the dome and the pith ball is varied, the angle, theta, at which the pith ball is hanging is measured. Then the electrostatic force is calculated. The table below contains the data. Wow, okay, they were actually very nice here. They gave us a lot of information. Let's just look at what we have to actually do. So using graphical analysis, we want to determine the experimental value of Coulomb's constant, K. As part of your response, complete the data table. Provide a graph of the electrostatic force as a function of the reciprocal of the square of the separation distance. Wow, that's very nice. They're even telling us how to straighten the graph. Determine the slope of your graph and relate the slope algebraically to a physics equation. So see, right, that is important. You have to actually do that step of showing why you're finding the slope. You can't just find the slope, right? That won't get you full marks, okay? State all necessary physics principles and formulas. Okay, so truth be told, this is a written response question from an old diploma. They've actually taken written response off of the diploma for Physics 30, but still, it's good for really getting a feeling for how this stuff works, what we're looking for, and they could totally incorporate all of these ideas and skills into a multiple choice or numeric question as well. All right, so taking a look here, let's just get a feeling for what's actually going on. How did they actually, how did they use that angle there? Not really mandatory for answering this question, to be honest, but, you know, good to think about the experiment that's happening. Well, okay, the ball is just being supported out here, right? But normally the ball wouldn't be like this. It would just want to hang downwards, right? So the force, the electric force from the dome must be pushing it off to the right, right? It must be repelling it away. Otherwise, why would it be hanging off to the side like this? Okay, so let's just draw a free body diagram. Think about the forces acting on this. We know there's the force of gravity, right? It's got mass, so the force of gravity should be pulling it downwards. And then clearly, the electrostatic force is pushing it to the right, repelling it that way. But the ball is not accelerating, right? It's supported out here. So think back to Physics 20. If the ball is not accelerating, that means the net force, the total force acting on it is 0, right? So we're actually just applying Newton's first law here, physics principle number 0 from your formula sheet. The net force on this ball needs to be 0. So there's a force pushing it to the right and a force pulling it down. There must be some force pulling it, you know, to cancel out that y force and that x force. And aha, sure enough, it would just be the tension in the rope, right? So that's the force of tension in the rope. We can see, okay, there we go. That has enough x component to cancel out the electric force. And I might have drawn it a little bit too big, but it's also, you know, got enough y component to cancel out that force of gravity. I'm just going to make the force a bit bigger. And just thinking about how this experiment would have been done, right? We can get the mass of the ball pretty easily, just weigh it. And then we know from Physics 20, the force of gravity is just mass times acceleration due to gravity. So actually, this is one that a VAD, if we draw a VAD here, right? We know we've got the electrostatic force pushing the pith ball to the right. We know we've got the force of tension pulling it up this way. And then we know the net force is 0, and sure enough, on our VAD, we get right back to where we started. So the net force is 0. FG, which is just mass times acceleration due to gravity. So actually, if we look here, we can see how these students would have used the data they collected to calculate what this electrostatic force actually was. Again, not really what the question's asking us to do, but good to understand the experiment, right? Because look, they measured this angle here, right? But if we just use some geometry here, we know this is a 90-degree angle, so we could do 90 minus that to figure out this angle here. They'd have to do some geometry, right? And then, hey, this is a right angle triangle, because that's vertical, that's horizontal. They make a 90-degree angle to each other, and all triangles add to 180. So 180 minus 90 minus this would give us this angle here. So we could use that angle there and think about that, right? We want to figure out what the electrostatic force is based on the stuff we were able to measure with just getting an angle, right? Just getting an angle and knowing the mass of the ball. Look, we want opposite, we have adjacent, so we could say tan of that angle there, which actually ends up being the same as this angle, to be honest, if you do the geometry on it. So tan of that angle will be equal to the electrostatic force over the force of gravity, opposite over adjacent. And therefore, the electrostatic force would just be Fg times the tan of theta. Anyway, just wanted to show how, because sometimes students are like, what are they telling us about an angle for, right? It's just applying the Newton's first law, stuff we learned in physics 20, right? If the ball's sitting out here supported, the forces acting on it must be balanced, right? And we can use that with the geometry there to figure out, all right, so exactly how strong is this being pushed by the electric force? Okay, now let's actually get into solving the problem at hand, now that we kind of have an understanding of how this angle was used to calculate the electrostatic force. Okay, we know, it shows us here, right? Using graphical analysis, we want to determine the experimental value of Coulomb's constant. We want to complete the data table. We'll do that in a second, but let's think about why they're asking us for this, the reciprocal of the square of the distance, okay? Because again, to use graphical analysis, we know we need a slope, area, or intercept. So if we just do this, FE as a function of their separation distance, they're calling it D, but typically we would call that R, still means the same thing. We know if we did this, we couldn't do graphical analysis, right? Sad face. But that's because the equation is this. And therefore the relationship is this between FE and the distance they're separated, right? Again, they're using D instead of R, but it means the same thing, how far apart they are, right? But like we just saw in the previous page there, that means FE as a function of 1 over R squared will make a straight graph. So that's why we're finding the reciprocal of the square of the distance. That's going to be what we put on our x-axis, so that when we plot the force as a function of this, we get a straight line. If we plotted the force as a function of this, we would get that inverse square shape, because this is inversely proportional to the square of this, which means it's directly proportional and linearly proportional to the reciprocal of the square, right? This is just 1 over R, or in this case, they're calling it D squared. That's all that is. That's why its units are meters to the minus 2, right? Meters to the minus 2 is just 1 over meters squared. Okay, so literally, we're going to take the distances, the D's, we're going to do 1 over them squared. So first up, 1 over 0.29 squared. That's going to give us 11.89. And now we've got at the first point that we're going to plot on our straightened graph. When x is 11.89, y will be 6.5, because we're putting 1 over r squared on the x-axis. Not r, 1 over r squared. All right, I'm just going to do that for all of these points now. Ready? So take the distance, 0.38 for our next one, do 1 over that squared, and that gave me 6.93. Next up, 1 over 0.5 squared, which is actually just 4. Okay, I'll do the last two here, but it's the same thing, just taking the distance and doing 1 over it squared so that that can become our new x variable, because this is linearly related to this, right? Giving us a straight line when we graph it. Okay, so next up, on the next page, we need to actually produce the graph and do some graphical analysis with it, okay? So we'll provide a graph of the electrostatic force as a function of the reciprocal of the square of the separation distance. So let's go ahead and fill in our graph. Now we need proper titles. Folks, a science or a physics graph is not the place to get creative with your titles, okay? That's for other classes. We actually don't get creative at all. It's always the same thing. Y as a function of x, responding as a function of manipulated. You say those actual variables, but that's it. So for us here, our y, our responding is electrostatic force. We're just going to say that as a function of our x variable. Our x variable here, careful, it's the reciprocal of the square of the distance. So it's going to be a bit of a mouthful, but that's what we always do. Y as a function of x. So electrostatic force as a function of, and that's really it, right? So responding as a function of manipulated. Y as a function of x, okay? All right, now proper titles on our axes as well. So what's going on our y-axis is the electrostatic force. So let's throw that in there. And can't forget the units, right? If you're making a graph, you have to tell people what does a square actually represent. In this case, our electrostatic force, we normally would do force in newtons, but in this case, all of our numbers are based on like times 10 to the negative 3 newtons, right? This is 6.5 times 10 to the negative 3, 3.7 times 10 to the negative 3. So it might not make much sense to scale it in newtons because then we'd have like, 0.0001, 0.0002, 0.0003. So that's okay. We can actually say the electrostatic force, but it's measured in times 10 to the negative 3 newtons. And then everyone will know, like if they see a 1 here on our y-axis, they know that we mean it's really 1 times 10 to the negative 3 newtons, right? This would be 4 times 10 to the negative 3 newtons, etc. Okay, now we got to label our x-axis. And to get a nice straight graph, that's what has to go on our x-axis, right? Again, not separation distance. That's not what we're about to put here. We're about to put 1 over the separation distance squared, right? Reciprocal of the square of the separation distance, okay? And units, what would those units be? Well, r, or d in this question, is measured in meters, right? So 1 over r squared is 1 over meters squared. Or we often just write that as meters to the minus 2. Right? The same way, in math, x to the minus 1 equals 1 over x works the same way in physics. So we've got units of meters to the minus 2. Okay, and they helped us out here by even showing us that in the table. All right, so next up, we just have to scale our axes, right? Meaning actually like put numbers on here so people know what the numbers mean and put numbers here so they know what we mean. When doing that, we don't want to just randomly start throwing out numbers, right? We should plan ahead a little bit. So like looking at our electrostatic force, we kind of want to spread out the graph a bit. Like we don't want to make this 10, for example, because then look, our largest value is only 6.5. So look at all the wasted space, and that's actually going to make it way harder to read and way harder for us to analyze. So spread it out, right? We can see that on the y-axis, we need, whoops, too far, sorry. On the y-axis, we need to go up to, about 6.5. So I'd say we're probably actually safe to just go like, just counting out here, I think we've got 10 squares, 10 big ticks. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So 6.5, I mean, that's pretty good. On the y-axis, getting to 6.5. I think rather than getting into weird decimals, let's just go up by ones on the y-axis. Okay, can't go up by 0.5s because then we wouldn't get high enough. We'd only get to 5 by the time we got here. And I think probably just going up by ones is better than going up by like 0.75 or something to try to get there, because then the numbers would be hard to work with. Now, on our x-axis, here is what we're working with once again, right? We're not plotting as a function of r, we're plotting as a function of 1 over r squared. So these are the x values I'm working with. So I need to go from, 0 up to about 12. Let's plan that out a bit. So here I can't go up by ones because once again I have 10 ticks to work with, right? And if I go up by ones for the major ticks, I'll only get to 10. I need to go higher than 10. I need to get up to 11.89. So I guess we could go up by 2's, right? 2 would be okay. That wouldn't be too bad. We'd have 2, 4, 6, 8, 10, 12. We'd still be using most of the graph area, so that's pretty good, right? It's probably worth it rather than trying to go up by 1.5's, which would be hard to work with. So let's do that. Let's go up by 2's on the x-axis. All right, now this is the fun part. We've set up the graph, we've scaled it all out. It's time to actually make it. Woohoo, that's the best part. So these are our points, right? When x is 11.89, y is going to be 6.5. So let's go find that on the graph. So when x is 11.89, which is pretty close to being 12, right? Like here's 10, 11 would be in the middle, 11.5 would be in the middle again, and then we're like 11.75 would be there. We're all the way at 11.89. So we're pretty close to 12. And when x is 11.89, pretty close to 12, y is supposed to be 6.5. So that's halfway between 6 and 7. So there's a point we can add to our graph. Right, there it is, just showing what FE is when the reciprocal of the square of the separation distance is 11.89. FE is a function of 1 over r squared. Okay, I'm just going to add all of these points now. So I'm going to do when x is 6.93, y is 3.7. Okay, so there's that point, right? X is 6.93, so just about halfway between 6 and 8, just about 7, right? And y is 3.7, right? So 3.2468, so halfway between 3.6 and 3.8, right? Okay, I'll just do the rest of the points here now. All I'm going to do, go through, when x is 4, y will be 2. When x is 2.3, y will be 1.2. I'm going to add those all in. And there's the result of plotting all those points. Do you see it? It's a straight line, right? I mean, ish, this is data. It's probably not perfect, but it's a fairly, definitely what's suggested by this is not, you know, a big curved relationship or a curved that way or an inverse. And that's because we plotted the force as a function of 1 over r squared instead of the force as a function of r, okay? So we've plotted our graph, right? Now we can't do much with this while it's individual data points. We need a line of best fit. Because remember, that line, again, it represents the trend in all of our data, right? If we were just to go, okay, run and rise and call it a day, right? Then why did we do all these other trials? They never got used. And then we better hope that these 2 trials were really good, right? Doing an experiment once is not a very reliable experiment, right? I mean, would you test out a new food if they told you, yeah, 1 person ate it and they were fine, right? No, those types of things get tested by lots of people. So we can't rely too much on a single data point. We want to get lots of data and then look at what the trend suggests, okay? So if I look here, right, first things first, visualize the line that represents that data. Can you kind of see the line roughly, right? And then lightly with a ruler, try to draw the line that represents it. Remember, the things you're looking for are about as many points above as below, that you're not forcing it through any point that you feel like it should go through, okay? And more than anything, you're trying to, again, represent the trend in the data, okay? A way to think about it is that if you draw the line, you're trying to minimize the total distance between the data points and the line itself. That one was just a rough go. I'm going to pull out my ruler and I'm going to do my best to draw a line of best fit here. All right, so is it perfect? Probably not, but I think it's pretty solid, right? I mean, we've got 2 points right on the line. This one pretty close to being on the line, and then one a little above, one a little below, right? And more than anything, when I step back, I say, yeah, you know what? That does represent the trend in the data pretty well, right? It's not like it looks like this or something where it really doesn't match what the data points were showing me. So now that we've got our graph, we're ready to analyze it. Okay, now remember, the whole point of this was to determine the experimental value of Coulomb's constant, K, right? Now, they were nice enough to tell us we were going to determine the slope of our graph to do that, but that doesn't mean that the answer is just going to be the slope, right? So let's let the equation tell us, first of all, why we're interested in the slope anyway, and also what we need to do with the slope. So like I said, graphical analysis, it's not about guessing, it's not about memorizing, it's about letting the equation guide the process. So the equation we're dealing with here is Coulomb's law, right? And so, like, looking at this, we want to use this equation with graphical analysis to find Coulomb's constant. Okay, so there's kind of two ways we could go at this. One thing we could do is just isolate for k and see what we're doing with y and x, right? We can see our y variable here. That's what's on our y-axis, right? And we can sort of see our x variable here. It might be more obvious if I rewrite this like this, right? This is the same as kqq times 1 over r squared. Let's just do that because now we can really see, okay, there's my x, there's my y. And so if I solve this for what I want, which is k, I would need to divide both sides by qq 1 over r squared, right? And now we can let this tell us what to do. We've isolated for what we want. Look at what we're doing with y and x, right? Here's my y variable, the electric force, right? Or rise. Here's my x variable, 1 over r squared, right? Or run. So this is really just saying that the Coulomb constant will be rise over qq times run, right? And rise over run, that's just slope. So we could think of this as 1 over qq times the slope, right? Or slope divided by the two charges. Now, what we have just done is this. We've related the slope algebraically to a physics equation, right? They didn't just want us to find the slope. They know that we've probably done Math 10. They know we can do rise over run. They want us to show them why the slope is related to this physics quantity that we're trying to solve, right? Using the equation. Okay, now I'll just show you an alternate approach here, one that I personally think is easier, and it's good to familiarize yourself with it because later, certain other equations, it becomes much easier to have this in your back pocket, okay? Remember that the equation of a line is just y equals mx plus b, where m is the symbol we use to represent the slope and b is our y-intercept. That makes sense because we know at the y-intercept x is 0, so if I make x 0, y will be b, right? When x is 0, y is b. That's just the definition of the x-intercept, right? It's just, for example, from math class, if we had the equation of this line, we could say, aha, this line will have a slope, a rise over run, of 3. It'll rise 3 when it runs 1. And it will have a y-intercept of 1, right? Y equals mx plus b. So this slope would be 3, this y-intercept would be 1. Okay, now what does this have to do with this? Well, it's a line. We're graphing a line. That was the whole point of straightening the graph. So if we were to write it in this form, we might be able to pick out how k relates to the slope potentially. So to write it in y equals mx plus b form, what has to be isolated? The y variable. Well, hey, we're in luck. In the equation, the y variable, the electric force, is already isolated. So we can see it coming together, right? So y equals, okay, this is mx, right? Well, x is in there, right? This is kqq times 1 over r squared. Maybe I'll rewrite it that way to make it even more obvious. Okay, and now we can really see it. So our y variable is isolated. This is the equation of a line. If we make y is fe, our x variable we know is 1 over r squared. So we have y equals stuff times x. What's that stuff then? That stuff is our slope. So this is m, the slope. Don't confuse it with mass. We're just using the math symbol m to mean slope, right? So think about what that means. We want to find k, and now we know that kqq is our slope. And therefore, what's k? K will be the slope divided by the charges multiplied together. And look at that. We get the same result as doing it the other way. Okay, so neither is better than the other necessarily, neither approach of thinking about it. They really are doing the same thing at the end of the day, but just wanted to show you both, right? It's good to remind yourself and be comfortable with the y equals mx plus b, but either way, what are we doing there? Again, I didn't memorize this, right? I didn't just pull this out of nowhere. I let the equation tell me why the slope is of interest and also what I need to do with the slope, right? It's not as simple as just calculating the slope. We have to calculate the slope and then divide it by the charges multiplied together. But that's not too bad because they gave us the charges, right? So there's our plan. Now that we've made our graph, we know we need to find its slope and then divide it by the product of the charges. So here we go. To get a slope, we need a rise and a run. To get a rise and a run, we need to find two good points that we can easily read and see how much it's actually rising and running. So just looking for some nice, easy to read points where I won't have to estimate. Ooh, look at that one. That's nice. I can read those directly off. So I'm going to use that point. And then I might actually go all the way down here to this point. That looks like the next best point. So I'm going to use that one right there. Or you know what? Yeah, no, I'm going to use that one. So because we have a nice straight line, we know we can use any 2 points on it. So we just need to figure out what is the run here between those. Well, it runs from there to there, right? And what's the rise? Looks like it rises from there to there, right? So now I can use my graph. I need to figure out, okay, what's the difference in y between here and here? So it looks like it ends up at 6 point, these are going up by 0.2s, 6.2468. Yeah, so 6.2, my rise will be 6.2. Now, don't forget about the times 10 to the minus 3, right? These aren't newtons. These are millinewtons. This is 6.2 times 10 to the minus 3 newtons. And it started from, looks like, 0.4 times 10 to the minus 3 newtons, meaning that it would have had to rise 5.8 times 10 to the negative 3 newtons between those points. Now, let's do the same for the run. So on the x-axis, since we're going up by 2 here, we're going up by 0.4 instead of 0.2 on the small grid lines, right? 10.4, 10.8, 11.2, 11.6, 12. So this is 11.6. So for the run, it went up to 11.6 on the x-axis, starting from, for my other point, 0.8. Giving me a run of 10.8 meters to the minus 2. Okay, so remember what we said. We said we could calculate the Coulomb's constant by getting the slope and dividing it by the product of the charges. So let's get the slope, and then we'll divide it by the product of the charges on the pith ball and the Van de Graaff generator. So slope is just rise over run. And from our graph, we got a rise of 5.8 times 10 to the negative 3 newtons, and a run of 10.8 inverse squared meters, okay? So divide those two and we'll get the slope. So I get that the slope is 5.37037037 times 10 to the negative 4. Our units would be newtons per inverse meters squared, but those dividing by meters to the minus 2 is the same as multiplying by meters squared. So we could just turn those into Newton meters squared. Okay, we're almost there. Remember what we found by looking at the equation. We said that K would be the slope divided by the two charges. Well, now we've got the slope and they gave us the two charges. So let's put them in. Exciting. So K is the slope we got, and then we're going to divide it by those two charges. I just went and wrote them down from the question. Remember, we don't use those negatives. That is a scalar. It's not talking about direction and force and all that stuff. We're just going to use the magnitude. So 2.0 times 10 to the negative 6 times 3.0 times 10 to the negative 6 coulombs. And here we go, moment of truth. Whoopsies, that would have been bad. Not times 10 to the negative 6. Go back and read the question. I even wrote it down correctly here, but wrong there. 10 to the negative 8 coulombs. That's my bad. Okay, now moment of truth. Wow, so when I put that in my calculator, I got 8.95 times 10 to the power of 9 Newton meters squared, right? Those would be my units. Newton meters squared per, we're dividing by coulombs times coulombs, so per coulomb squared. Not a bad result at all, right? We know the actual theoretical value of the Coulomb constant is 8.99 times 10 to the power of 9. So we're off by a very small amount, right? Truth be told, I've done this question quite a few times, like throughout the years, and I always do it live. I draw my own line of best fit and everything. That's probably the best result I've ever got. I'm usually closer to like 8.8 or 9.01 or something like that. That's pretty good. Okay, so not a bad result. We got the right units. We are pretty close in terms of the actual numerical value, and we used our graphical analysis to do so. Okay, so I know that's a long question, right? But it's just applying those ideas. Again, using the equation to tell us what characteristic of the graph we need and how we need to use it. Then we just draw our graph after straightening it so that we can get a straight line, right? Graph, put 1 over r squared on the x-axis instead of r so that we don't get a graph like this that we can't find the slope or area of, right? Instead, do fe 1 over r squared so we get a line like this that we can find the slope of. Then let the equation tell us what to do with the slope. Find the slope like we're back in Math 10 and divide by the charges like the equation told us to. Cool, right? Very satisfying. All right. Now we'll finish up this lesson not talking about anything new, okay, just again applying it in slightly, more complex situations. So it's still just Coulomb's law, it's still just forces acting on an object, all the stuff we've done before, okay, just applying it now in more scenarios. So of course there can be more than just two charged objects exerting forces on one another, right? Like so far we've had, okay, you've got, for example, a proton and an electron. But there's nothing stopping. Of course, there's definitely situations where you might have a proton, an electron, and another proton maybe, right? So that doesn't change anything about what we're doing because it still, if we were to ask what's the force acting on the electron, let's say, well, it's feeling a force of attraction from this proton, right? And it's feeling a force of attraction from this proton. If we knew the distances between them, right? If we knew these distances, we could calculate the force that this one's exerting on the electron, and we could calculate the force that this one's exerting on the electron. And then we know from physics 20, if multiple forces are acting on an object, well, that's just multiple vectors, right? We can add up those forces using all our usual principles of vector analysis, right? So it's almost like what we do is we say, okay, first, let's just pretend that one doesn't exist and figure out what the force would be pulling on the electron there. Then let's pretend this one doesn't exist and figure out what the force would be on the electron from that one, right? And then once we've got those two forces, they're both acting on the electron. So two things are pulling on it. Those forces are going to add, and we can add them up using the same principles of vector addition we always use, because force is a vector after all. Okay, so more than one charged object feeling forces from each other, no worries. We can calculate them all with Coulomb's law, and then we can add them up. We know from physics 20 that when multiple forces act on one object, they add up. And so the net force on any of the objects can be determined, right? So I recommend for these, determine which object you're finding the force on. I sometimes say, put yourself in that charge's shoes, right? Because of course it's different for this proton than it is for this electron, right? This proton is feeling a force of repulsion from this proton, right? Like charges repel. So this one would be feeling pushed this way by that proton, but at the same time pulled this way by that electron. So it's very important in these to first determine which charge are you actually being asked to think about, right? It would even be different for this one. Again, it would be being pushed to the right by this proton and pulled to the right by this electron. So it's different for depending on which charge's perspective you're looking at it from. So always make sure you figure out which object are you trying to find the force on. And then just Coulomb's law it, right? Calculate the force between it and each of the other objects separately with Coulomb's law. So we could do kqq over r squared for these two, and then kqq over r squared for these two if we were trying to find the total force on this electron, right? Because those are the two forces acting on it, the electrostatic force of attraction from this proton and from this proton. Okay, and then that's that's really it. We add the forces up after that, right? Coulomb's law, out all the forces and then add them up, but be very careful about are they the forces in the same direction or in the opposite direction, right? Because when we add those forces, if they're in opposite directions, we need to give them opposite signs. They'll be canceling each other out. For example, if we were calculating the force on this proton, it's being pushed to the left by this proton, but pulled to the right by the electron. So those two, it's kind of in a tug of war, right? The fact that this is pulling it to the right is going to make the net force a little bit smaller because it's canceling out with the push from this proton to the left. So you got to be careful about that. Diagrams, especially VADs, vector addition diagrams, are super helpful, right? I mean, no surprise there. We know that whenever we add vectors, vector addition diagrams can really help us out. Okay, let's just try out an example. So 3 identical charges of -6 millicoulombs are placed in a row from left to right, separated by a distance of 2.3 millimeters. Determine the electrostatic force acting on the object on the far left. Okay, so that's important. We're putting ourselves in that charge's shoes. Let's just draw a picture. All right, so 3 identical charges, each with the same charge. I just gave them some numbers here. Let's call it charge 1, charge 2, charge 3, but they all have the same charge, -6 millicoulombs. They're each separated by a distance of 2.3 millimeters. So let's add that in. We know that'll be important for calculating the force they exert on each other. Now I'm just going to call this distance R12. You can hopefully see why, right? It's the distance between charge 1 and 2. It is 2.3 millimeters. So 2.3 millimeters, right? And then this distance I'll call R23, again, because it's the distance between charge 2 and 3. And that's also 2.3 millimeters. Okay, so now let's start thinking here. We want to determine the electrostatic force acting on the object on the far left. So we're interested in the net force acting on this one, right? Which is going to be different than the net force acting on this one, which is going to be different than the net force acting on this one, right? This one, what's going on with it? Well, there's 2 negative charges over here. So these are both repelling it, right? This one is going to be repelling it, pushing it to the left, right? If this is feeling a repulsive force, it's going to get pushed to the left. So we'll call that F12, F12, the force on object 1 from object 2, the electrostatic force of repulsion, okay? And then also, I mean, this is negative, like charges repel, so this is also going to be pushing it to the left, right? This is also repelling it. So see what I mean? Basically, think about, okay, what if this one wasn't here? What would this one be doing to object 1? And then what if that one wasn't there? What would this one be doing? I mean, even though they are there, that's what we're doing, but we're just treating those cases separately. Now, there's something important to notice here, okay? Be careful. What is the distance between object 1 and object 3? We know we're going to need that to calculate the force, right? Is it 2.3 millimeters? No, right? Careful. It's actually double that, right? It's 2 distances of 2.3 millimeters. So R13 is actually 4.6 millimeters. Okay, so the third charge is actually twice as far from this one, right? So hey, we can actually make a prediction and we can represent it on our diagram here. If it's 2 times farther, what does that mean for the force that it feels? First of all, stronger or weaker than the force it feels from object 2? Weaker, right? Inversely proportional to the distance. And by what factor? Right, it's going to be 1/4 as large, right? 4 times weaker, because double the distance, it's an inverse square relationship. So I'm going to draw F13 about 1/4 as large as F12. Obviously, that's not, it's not like if I don't do it that way, I'll get the wrong answer or anything, but it's a good way to just keep track and keep our heads in the right place on this, right? Predicting what we're expecting to find accurately. Okay, so just to draw a free body diagram to just think about the forces on charge 1, right? We've got two forces to the left. So we've got F12 and we've got F13, which we're expecting to be about a quarter. By the way, one way we can show that we mean this is 1/4 the size of that, is we just split it up. So we say that's 1, 2, 3, 4. And since we've shown 4 sections there, what we're indicating is that 4 of these would fit into that. That's one way we can visually represent it. Let's draw a vector addition diagram for the net force on object 1, right? Well, it's feeling a force of repulsion to the left from object 2, we'll call that F12, and then another force that's smaller, but also of repulsion and also to the left from object 3. And so we can see that our net force, F net on object 1, right, is just from where we started to where we finished, right? Vector addition diagram, add them up tip to tail, and then the resultant vector, in this case the net force, is drawn from where we started to finish. Okay, so the things we can notice here, they're both in the same direction, right? They're both to the left. I might actually, since they're both that way, let's actually define that direction as positive and this direction is negative. Remember, there's nothing special about left that makes it negative or anything, right? It's just that we have to give opposite directions opposite signs. So I'm going to call that direction positive because both of my vectors I need to add are that way. So why add unnecessary negatives? Okay, now we're ready to go, right? We've got Q, and then we've got Q, and we've got the distance between charge 1 and 2, and we've got the distance between charge 1 and 3. So we can calculate each of these forces, and then we'll just have to add them up to find the total force on object 1. So that's our game plan. Ready? So the force that object 1 feels because of object 2 is going to be equal to K, Coulomb's constant, times the charge of object 1 times the charge of object 2 over the distance between them, R1, 2, squared. Okay, and we've got all those numbers, so let's put them in. All right, there we go. Coulomb's constant times the charge of object 1, charge of object 2, divided by the distance between them squared. Just be very careful, right? We need them in standard units. So we were given the charges in millicoulombs. Milli, remember, means times 10 to the negative 3. That's on the back of your formula sheet. Or you could have also just, divided by 1,000 to get 0.006. That's the same as times 10 to the negative 3 anyway, right? And same goes for our distance in millimeters. We need to convert that to meters. So 2.3 times 10 to the negative 3 meters, right? Coulomb's constant, K, is not set up to work with millicoulombs or millimeters. It's in meters and coulombs, okay? So our charge needs to be in coulombs and our distance needs to be in meters. Anyway, calculating that all out, I got that the force on object 1 from object 2 was 6.11796 times 10 to the 10 newtons, okay? And it would be to the left. And we can actually say left because it said in a row from left to right. So that direction, the direction of that force is to the left. Remember, important to think about direction for a vector like force, right? So notice the math didn't give me that, right? I had to think about it. It's not like it came out, with the right sign or anything and I knew that meant left. I had to put myself in the shoes of charge 1 and think about which way would charge 2 be pushing it, right? And if that's to the left, okay? So when I go to add them up, I'm calling left positive. I'll make that force positive. Okay. Now what we got to just do the same thing for the force from object 3. So I'm going to do the exact same thing. Here we go. And now the two charges I'm going to use to find that force are, of course, charge 1's charge and charge 3's charge. Happen to be the same here, but those are the two objects we're calculating the force between. And then use their separation distance squared, right? So it'll be the 4.6 millimeters, not the 2.3. Okay, let's put in those numbers and calculate. And that's what I got there, okay? Same result, just a different distance separating them there, okay? And look, this is a good sign because remember what we predicted. We said since object 3 is about twice as far from object 1 as object 2 is, right? Well, the force from object 3 on object 1 then should be about 1/4 as large because of the inverse square law, right? And sure enough, 1.5 is about 1/4 of 6. So yeah, we got about 1/4 of the result. Okay, that's a good feeling. That checks out with what we predicted. All right, so now we know how hard object 2 would be repelling object 1, and now we know how hard object 3 would be repelling object 1. They're both pushing to the left, so all that's left to do is what we visually did here, add up those forces and find the total force. So luckily for us, these are both in the same axis. That won't always be the case, but they're both in the same axis, so we really can just add them algebraically. Add this to this. I'm going to make that direction positive again since they're both to the left, and then I just know that a positive result means it's to the left. So F net 1, they're both in the same axis, so it's going to be the force from object 2 plus the force from object 3 on object 1, and we've got those numbers. Let's add them up. The forces are in the same direction, so I give them the same sign. I got 7.64746 times 10 to the 10 newtons. Okay, now we got a positive answer, which we defined as left, so that's good. We were definitely predicting a net force on object 1 being to the left. And now just significant digits, right? So we get 2 significant digits, so I would write this as 7.6 times 10 to the 10 newtons to the left. That is the net force on object 1. Okay, now it would be different on object 2 because that's being pushed to the right by object 1's repulsion and pushed to the left by object 3's repulsion, right? In fact, since they're equally distant and equally charged, you might be able to figure out that object 2 would feel 0 net force. It would be pushed just as hard to the right by object 1 as it's being pushed to the left by object 3, right? So this is the net force on object 1 that we've found. Different scenario for the other one. So you can see why it's so important to first just figure out which object are we finding the net force on. It'll be different for different objects when there's more than 2 charges involved. Okie doke, let's try another one. So in this one, 3 objects are placed in a line from left to right with charges of negative 10 microcoulombs, 16 microcoulombs, and 8 microcoulombs respectively. They are each 10 centimeters apart. Before the objects are allowed to move, a wire is used to temporarily connect the objects on the far left and far right. Ooh, that's important because that puts them essentially in contact, right? They have a conducting path between them. So electrons are going to want to move from one to the other in order to even out the charges, right? So we'll have to take that into consideration before we start calculating the actual net forces because the charges are going to change when we do that. All right, if the middle charge has a mass of that, what will be the magnitude and direction of its acceleration the instant it is released? Okay, well, to find its acceleration, we know from physics 20, we need to find the net force acting on it anyway, right? So it's really the same thing, just with the extra step of once we get the net force, we'll divide by the mass. Okay, let's start with a picture of how things looked before that wire got involved. So here's what we had before the wire, right? Negative 10 microcoulombs, 16, 8 microcoulombs. But then we touched the far left and the right one, right? I mean, you might not think, hey, we didn't touch them, but we kind of did. We allowed them to be connected by a conductive piece of wire, right? And if it's conductive, it allows electrons to flow through it. And electrons would want to move from this negative one, where there's obviously lots of extra electrons, to this positive one, right? Like would repel over here, and the opposite would attract the electrons over here. So electrons are going to move from there to there. Now, how do we figure out what charge those objects end up with after the electrons finish transferring? We'll think back to yesterday's lesson, right? When will electrons stop transferring? When this one is no longer any more attractive to them than this one, right? Every time an electron leaves here, this gets a little more positive and therefore a little less repulsive. Every time an electron arrives here, this gets a little less positive and therefore a little less attractive. And eventually, they have the same charge. This one has gained enough electrons and this one has lost enough electrons where they've met in the middle. So those two charges really do meet in whatever the middle of negative 10 microcoulombs and positive 8 microcoulombs is, right? The average of those two. So we just need to average them out. So we'll take negative 10 microcoulombs plus 8 microcoulombs and divide it by 2, because there's 2 objects there, to find the midpoint there. And when we do that, we get, well, -1 microcoulombs, right? It's -2 over 2. So they will meet at -1 microcoulombs, which means now our situation is no longer this, right? But said before they are released, we touch them. So what we're actually starting from in terms of finding the force and then the acceleration that's acting on it is this now. These now have charges of -1 microcoulomb each. Now, did anything touch this middle one? Did this have any reason to change its charge? No, so it's still 16 microcoulombs. And then they tell us that the distance between them is they are each 10 centimeters apart. So let's add that to our diagram. Okay, and so this is really what happens, what we're starting from when we release them. Now we want to know the magnitude and direction of the acceleration of the middle charge. So what we labeled as charge 2, right? So put yourself in charge 2's shoes. What's it going to be feeling? Well, it's positive and there's a negative charge over here. So it's going to be attracted that way because of charge 3, right? We can call that F23, the force on charge 2 because of charge 3. And then what would it be feeling because of this one? Well, hang on a sec. This one's also negative. So it's going to be attracted to the left by this one. So object 1 will be pulling object 2 to the left. And we can actually notice something here, right? Do you see it? These have the same charges, and it's the same distance away for each of them to object 2, right? They're both 10 centimeters away, and they both have charges of -1 microcoulombs. So when we go to do the calculation for the force from object 1, we're going to do K QQ over R squared. And then when we go to do the force from object 3 on object 2, we'll do K times QQ over R squared. Notice anything? The K, the Q and the Q and the R are the same for both of those calculations. So we can notice that and say, well, hang on a sec. This force is going to be the exact same magnitude as this force, but they're in opposite directions. So what does that mean for the forces? How will they add together? They're the exact same size, but they're in opposite directions? Well, they're going to cancel each other out perfectly, right? When we go to add them, we'll make one positive and one negative, but they'll be the same size. So that's okay to notice something like that and write a little verbal explanation. Don't be scared of using your words in your solution, right? We could say that the electric force is KQQ over R squared, and Q, Q, and R are all identical when we're calculating it for force 1, 2 and force 2, 3. Whoops, I said 1, 3 there, 2, 3, right? And then we could say that therefore the magnitude of this force is the exact same as the magnitude of this force. However, they are in opposite directions. So when we add them up, they'll cancel each other out. We're pulling this one just as hard to the left as we are to the right. So the net force, and therefore the acceleration of mass of charge 2, will be 0. Right? Showing that visually with a vector addition diagram there. However, force 3 is pulling object 2 to the right. Object 1 is pulling it to the left. So adding those up tip to tail, they perfectly cancel each other out. So our net force on charge 2 will be 0 newtons. And we know from physics 20, if the net force acting on something is 0 newtons, its acceleration is 0 meters per second squared. The equation backs us up there. If I put in a 0 as F net, of course I get a 0 as my acceleration, right? Just Newton's first law, okay? I'll just show the calculations here of force 2, 3 and force 1, 2 in case you don't believe me or you really want to calculate it out yourself and see. I'll just show those calculations here so you can confirm. But I want to emphasize, it is okay if you notice things like this and you explain yourself, right? That's okay. You don't necessarily need to make the calculation. Just jumping straight to 0 from here wouldn't be enough. But this is an explanation of why we can see and reason without having to calculate that the acceleration will be 0. But let me show the calculations. Okay, so I've gone ahead and calculated each force, right? The force on object 2 from object 1. using the charges and their separation distance squared, using the fact that micro means times 10 to the minus 6, right? That's on the back of your formula sheet, and divided by their distance squared, converted the centimeters into meters, okay? So there we go. There's the calculation. I get this is the force. And from thinking about it, again, that's not going to come out of the math, but we know that because this is negative and it's to the left of this positive, this is going to be attracted to the left. So that force on it will be to the left. Now you can really see here why it ends up being the same number, right? I'm going to put in, to calculate force 2, 3, I'm going to put in object 2's charge, object 3's charge as my Q and my Q. But those are the same as object 1's charge and object 2's charge, right? The same numbers, okay? And the same separation distance. So of course we get the same force in the end. The only difference is that this force is to the right, because this is a negative charge and object 2 is positive, so it's going to feel an attractive force to the right. Now all that's left to do is add them up, and you can probably see where this is headed. I just need to add these two forces up. They're in the same axis, so I don't need to worry about x or y components. I really can just add them vectorially, algebraically, but I need to be careful. They're vectors, right? So I need to be careful about my signs, and I need to make sure opposite directions have opposite signs. So when I put in force from object 1 on object 2, it's to the left, so I'm going to choose to make that negative, and then I'll choose to make this one positive because it's to the right. Right? A pull to the right and a pull to the left are opposite directions. So here we go. Sure enough, right? Negative 14.384 plus positive 14.384 is 0 newtons. So the acceleration will also be 0. If the net force acting on an object is 0 newtons, then its acceleration will be 0 meters per second squared. Okay, now again, I don't want you thinking that means every single object has a net force of 0 on it in this system. That's not true, right? Object 2 does, but object 1, think about it. It would be feeling repelled to the left by this, but much more weakly than it's being attracted to the right by this, right? This has not only a much bigger charge, it's also much closer. So object 1 would accelerate towards object 2. It would have a net force on it. And same goes for object 3, except the bigger attractive force would be to the left, right? So for object 1, it might look something like this. It is being repelled by object 3, but much more strongly it's being attracted by object 2. So remember, it all depends on which object we're finding the net force on. But it happens that this one ends up with a net force of 0. Okay, so go ahead and give this one a shot. And as always, I encourage you, right, pause, do more practice than just this one. But this is just kind of my recommended starting question while it's fresh in your brain. Take a little break from my voice, try a couple of these out. And if you hit any that are two-dimensional, that would be a good time to come back to the video lesson, because that's the last thing we're going to talk about here, where it's not just they're all straight in a line, but maybe there's some X and Y components going on. But hey, we know how to deal with that, right? Like I said, in physics, we don't really like, it's applying the same skills to new contexts. So we're just going to do all the stuff you've always done before, but now the vector that we're adding in 2 dimensions is an electric force. All right, so let's go two-dimensional with this, and then we'll be finished with this lesson and with this chapter, okay? But it's nothing new in terms of skills or ideas. I mean, I guess in terms of ideas, the new idea is that it's an electric force. But you've done this since Physics 20, right? First, you did it with displacement. Someone goes on a walk east and north, or at an angle north of east, right? What's their resultant displacement? Then you did it with forces. Something was pushed at an angle, right? Two objects or two forces were acting on it, each with X and Y components. Add them up. How did you do that, right? Then you did it with velocities, and you've done it with lots of different vectors. In fact, this isn't even a new vector. It's just a force. The only difference is the source of that force is an electrostatic force, right? But the principles are the same. So like you would have done in Physics 20, draw your vector addition diagrams, right? Assign signs to each direction, your positive Y direction, your negative Y direction, positive X, negative Y, okay? Separate each vector into its X and Y components, because you need to do that to be able to add them up, right? The same way walking east doesn't cancel with walking north, right? An electric force to the right doesn't cancel with an electric force upwards, right? Only right-left can cancel, or up-down. That's why we need to separate them into x and y components so that we can add x's to x's and y's to y's. And then we add up all the x's, and that gives us the x component of the resultant vector, right? We add up all the y components of the resultant vector, and that gives us, we add up the y components of each vector, and that gives us the y component of the resultant vector. Okay? Essentially, what we're trying to do is build this triangle. Trying to find the net force acting on an object, right? Well, we can find the net force's x component by adding up the x component of every force that's acting on it, right? Add up F1x plus F2x plus F3x plus, if there's more, keep going, right? Paying attention to opposite signs, or opposite directions getting opposite signs, right? And then we need to find its y component. How do we get that? You guessed it, we're going to add up F1's y component and F2's y component and F3's y component. And if there's more, add those in as well, right? This is the whole idea behind two-dimensional vector addition. We want to essentially build this triangle one side at a time, right? And in order to do that, we need to get its x component by adding up the x component of every force that's involved. And to get its y component, the net y force, we add up the y components of every force that's involved. Then we'll have these two sides. How can we get this side? With the Pythagorean theorem, right? So use the Pythagorean theorem with the x and y components of the resultant to find the resultant vector itself, right? If you know the net force in the x-axis and the net force in the y-axis, you can use Pythagorean theorem to find the overall net force. And the last missing piece, net force is a force, so it's a vector, so we can use trigonometry to get the direction, which will often be an angle. Okay, so that's all we're going to do. The one new thing here for Physics 30 from how you've done this every other time in your life is that these will be calculated with KQQ over R squared first, right? Or rather, F1 itself will be calculated with KQQ over R squared, and then you'll find its x component with SOHCAHTOA, right? So maybe F1 is something like KQQ over R squared. And from there, once you've calculated F1, it's all the same stuff. This would be its x component. This would be its y component. Maybe you're given its angle, so you can use trigonometry to find those x and y components, right? And then do that for every force you have that's acting on the object. Add up all the x's, add up all the y's, Pythagorean those to get the net force itself, and trigonometry to get the direction of the net force. Okay, so it's the same idea. The only new thing here is that the resultant vector we're looking for is just the net electrostatic force on the object, right? F electric net. The vectors we're adding to find that are just the individual electrostatic forces from each charged object. So it's the same thing we were doing before. We're going to find the forces, add them up. It's just that now that adding them up part might involve vectors in 2 dimensions. So let's try this one out, see how it goes. So a -6 nanocoulomb object has a 12 nanocoulomb object 20 micrometers to the right and a -18 nanocoulomb object 15 micrometers below it. We want to determine the magnitude and direction of the net force on the -6 nanocoulomb object. Okay, let's definitely draw this out because it's kind of hard to picture, isn't it? So we've got a -6 nanocoulomb object with a 12 nanocoulomb object 20 micrometers to its right. Let's start there. All right, so I'm going to call those 1 and 2, and object 1, the -6 nanocoulomb. Again, nano means times 10 to the -9. That's on the back of your formula sheet. It's 20 micrometers to the right, and micro means times 10 to the -6. So the distance between objects 1 and 2 is 20 micrometers, or 20 times 10 to the -6 meters. All right, but that's not all, because then there is a -18 nanocoulomb object 15 micrometers below this. Okay, so let's add that to our diagram. So there it is below, and it's below by a distance of what we'll call R13, going to call that charge 3. 15 micrometers. So 15 times 10 to the negative 6 meters. Okay, so you can see we've got all the stuff we would need to calculate the force on this from object 3, right? We've got Q, Q, and R. And same goes here. We've got Q, Q, and R. So we could calculate the force from object 2 on object 1, and we could calculate the force from object 3 on object 1. And that's the physics 30 part. From there, it's a physics 20 question. We just have to add those forces up, right? And they're two forces in two different dimensions. Okay, let's just first get our bearings here and think about what the forces look like. Okay, so like always, right, one at a time, think about how these charges would be affecting this charge, because that's the one that we're interested in finding the direction of the net force on, right? Again, different story for this and for this, but for this one, okay, what is the direction, what are the forces from object 2 and from object 3? How do they add to give us the net force on it? Well, okay, object 2 is positive 12 nanocoulombs, and object 1 is negative. So are those two attracted or repelled? They're attracted. Opposites attract, right? And so for object 1, what does that mean? Is it pulled to the right by object 2, or is it pushed to the left? It's pulled to the right in this case, right? Okay, so that's an x-axis force. So that is, roughly what F12 looks like. It's a pull to the right, an attractive pull. Now, reset and ask yourself, all right, great, that's the force from object 2, but what's the force from object 3 on object 1? Well, this one is negative, and this one is negative. So, attraction or repulsion? Repulsion, like repel, exactly. And what does that mean? Which way will object 1 actually be getting pushed by object 3? It'll feel an electrostatic repulsion upwards, right? Because 3 is below it. So it's a little bit, it'll be bigger actually, we can tell, because not only are they closer together, but this one has more charge than object 2. So hard to super accurately draw it, but upwards and, a little bigger. Okay, that's what the force from object 3 on object 1 will look like. And there we go. Now we kind of have an idea, right? Let's draw a vector addition diagram. So what are the forces it's feeling? Well, it's feeling F12 to the right. So let's draw that first. Again, the order we draw them doesn't actually matter. Okay, and then tip to tail, let's draw this upward force. So we're going to add this force, this y-axis force, to that one, tip to tail. And those are the only two forces acting on object 1. So what's the net force acting on them? Well, same as always, to draw the resultant vector from where you started to where you finished. And unsurprisingly, the net force on object 1, I'll call it Fnet 1, is kind of uppy lefty, right? Because it's being pushed up by this one's repulsion and pulled right by this one's attraction. Okay, so there we go. And this actually, we can see here, this actually ended up being a not too bad one, because these are perpendicular to each other. Now that won't always be the case. Sometimes you will have to separate this force into its x and y components, right? For example, if we were asked to find the force on object 2, well then the force from object 3 on object 2 would look something like that. Right? I guess it would actually look like this. It would be attractive like that. And then we'd have to take that and split it into its x and its y, which we could do. It'd be a little more work, but it's nothing we couldn't handle, having completed physics 20. But in this case, we're actually not even going to have to do that, because look, if we calculate this force, and then we calculate this force, we'll already have F net x and F net y, right? So let's just go ahead and jump in. We can just go ahead and say, all right, like step 1, let's find those forces, and then we can worry about, adding them up as we always add up vectors. So first, let's just find F12 with Coulomb's law. So there we go, right? That's how we calculate the force with Coulomb's law. Let's plug in the numbers for force 1, 2. So just using the charge of object 1 and the charge of object 2 and their separation distance, okay, I'm calculating that force would be 1,618.2 newtons. Okay, now by thinking about it, we know that the direction is to the right, or we could say it's at 0 degrees. That might be more helpful now that we're working in 2 dimensions to call it 0 degrees, right? The positive x direction, or to the right of the x-axis. So force 1, 2 is 1,618.2 newtons at 0 degrees or to the right. Okay, so keeping our eye on the ball here, right? Now we've got this. If we could just get this, we'd only have to do Pythagorean theorem to get the net force on object 1. So here we go. Step 2, let's find F13. So same idea, use Coulomb's law, but now obviously plug in charge 1's charge and charge 3's charge and their separation distance. And that gives me 4,315.2 newtons when I plug in those numbers. Okay, now what about the direction? I mean, we could say up. We could also say like 90 degrees, right? 0, 90. I might just go with 90 here. So the force of object 3 on object 1 is going to be 4,315.2 newtons. I know that looks rounded. It's actually not. That is actually what your calculator gives you. Okay, so there we go. Now, keeping our eye on the big picture, we've got these two sides of a right angle triangle. All that's left to do to actually figure out the net force is to use Pythagorean theorem, right? This squared plus this squared will equal this squared. And then we can use trigonometry to actually describe its direction. So here we go. Okay, and so again, right, we're doing the same thing as always. Find the net x force. It's just that in this case, we got kind of lucky, and there's only one force with an x component, and it's all x, right? It's just F12. I mean, how would we find F net x? We would add F12x plus F13x, right? The x force, the x components of each force. Well, F13x is 0, and F12x, well, F12 is all in the x-axis, right? So that's why they're the same. And same idea here with F net y, except there's only one force with a y component, and it's all in the y-axis. Again, that won't be the case for every question you do, but you still know how to do it, right? You split them into their x and y components with trigonometry, then add those x components up to get F net x. It's just that here there was only one thing to add, and we didn't have to split it into components. Okay, so now we know this about F net on object 1. We know that its x component is just the force from object 2 on it, and we know that its y component is just the force from object 3 on it. Okay, so with our little diagram here, we are ready to find F net with the Pythagorean theorem. So here we go. F net x squared is just F net 1, 2. So, or sorry, F12, so 1,618.2 newtons squared. F net y is just the force from object 3 pushing it up. So that will be 4,315.2 newtons. Okay, we'll square that. We're doing the Pythagorean theorem, right? This is why the diagram helps. We can see why we need the Pythagorean theorem here. And then that gives us that the net force on object 1, its magnitude anyway, is... it's 4,608.64 newtons. Okay, now we're almost done, but it's a force, it's a vector. So is that a complete answer? No, we also need to give direction. Can we just say uppy righty? No, that's not good enough, right? We need to actually give an angle. What angle is this pointed at? Okay, well, good thing we've drawn our diagram because that lets us see pretty easily the angle we can use to describe its direction. So last step, let's get the direction of the net force, and then we'll be able to actually say which way it's pointed. So looking here, again, nice thing about having your diagram drawn is it's really easy to see. Okay, so opposite, I've got, adjacent, I've got. I can find that angle pretty quickly with tan. So the tan of theta equals 4,315.2 over 1,618.2, just opposite over adjacent there. And therefore, theta itself is the inverse tan of that ratio. And that gave me that angle there was 69 degrees. Okay, now, always be careful with those, right? Do we actually mean 69 degrees, right? Because we're just getting that angle there. But I think in this case, yes, we're actually safe, right? Because we think of this as 0. We rotate counterclockwise, so we get 90, 180, right? So we actually do mean, if we look at that, and then we look at our angle here, we really do mean from the horizontal counterclockwise 69 degrees would get you so that you're pointing the direction of F net on object 1, right? So we could actually just say 69 degrees. We don't need to do like 180 minus or 360 minus or something like that to properly communicate the direction. So here we go to the correct number of significant digits, and with direction, the net force on object 1 is 4.6 times 10 to the 3 newtons at 69 degrees, okay? So it's all the same principles, right? Here's the physics 30 part. This was the whole thing that involved actual physics 30 concepts, right? The rest was physics 20, adding up vectors in 2 dimensions, right? The new thing that we learned this year, or in this, whenever you're taking this class, right, was how to calculate electrostatic forces using Coulomb's law. Okay, but other than that, it was the same old, same old. Okay, so what I really encourage you to do now, yes, there's a practice question there, but I would really encourage you to go and actually just read through this example, okay, from your textbook. Your textbook's actually, I like your textbook. I find it does a really good job. Be grateful for that, because not all textbooks do, but I find the physics textbook does a nice job of showing its work and explaining what it's doing. Okay, so the reason I highly recommend you do this one is that it involves one where, you know, like I was saying for object 2, if we were to have to do this question for object 2, right? And it wouldn't be as straightforward. I mean, we could still handle it, but in that case, the force from object 3 would be at an angle, so we'd have to split that into its x and its y components, then add up the x component of that with the x component it feels from object 1, right, to get F net x, then do the same in the y-axis, and then Pythagorean, and then SOHCAHTOA. So similar process, but an extra step of actually having to separate into x components and add up multiple x components. So this example is like that. So I really do encourage you to read through it. And if there's any steps that are like, I'm not sure, right? Either or both, right? Try working through them. See if you can, you know, that's how we learn, right? We struggle through a concept that's maybe giving us some trouble at first. And if you really get stuck, if you're really not sure about it, of course, always I'm happy to help, right? Reach out to me, book a meeting, whatever it might be. So I would encourage you to go do that, right? And then, of course, this practice question is my recommended starting point, and the rest of the practice work for chapter 10 now, of course, you can do as well, because we are finished chapter 10. So that wraps up the second chapter of Physics 30. We are not done with the second unit, okay? We still have to do chapter 11 and 12, but this finishes the first chapter of Unit B, so you can go ahead and actually do your chapter 10 quiz once you've practiced and reached out for questions and all that good stuff, okay? And in the next lesson, we'll be on to chapter 11.